Yes. Hi, good afternoon. Good
Uh,
evening.
Okay, so let me just share my screen and we'll be starting on with this session. So yeah. Okay, I hope my screen is clearly visible to everyone.
Yep.
Okay, fine, thank you. Okay. So today we are live on YouTube as well. So I'll be simultaneously reading down the yeah. So okay, yeah. So let's start with today's session. So in today's session, what we are going to do basically, we are going to have a lot of discussion about recursion, right? And we'll be understanding like basically how recursion takes place, like how the process of recursion looks like, and we'll be understanding it, and we'll be doing the dry run of each and every question, like which we'll be seeing on. Okay, so let's begin today's session. And before that, I'll be just showing you what is today's agenda. So yeah, in today's session, we'll be discussing this many things. So we'll be having a discussion about what is recursion and what are the points that you should keep in mind while doing recursion. And we'll be seeing on a few basic recursion codes, right? And we'll be also seeing out different questions that are related to recursion. So I hope today's agenda is clear to everyone.
Yes.
Okay. And one more thing, like in today's session, we'll be seeing recursion, right? And in the upcoming session, the next session which we are having tomorrow, right? It is on backtracking. So backtracking and recursion, they basically go parallel to each other, right? So there is not a lot of difference between backtracking and recursion. And in tomorrow's session, we'll be focusing, basically, we'll be seeing different questions related to backtracking and how to write down what is the difference between recursion and backtracking. So that is going to be what we'll be discussing in tomorrow's session. Okay, so let's start with today's session. And first of all, let's before moving on with the recursion, first of all, I would like to give you an example. Like, let's say I have a main method. Okay, and inside this main method, what I'm going to do, I'm going to call a function fun, and here is my function fun. Okay, so what is taking place? What is happening over here? Basically, there is a main function, and the main function is making a call to some other function that is fun. Now, what is recursion over here? Basically, what is the difference between recursion and a function calling it itself? Like basically, the function calling other function. So now let's say instead of main calling function, what I'm going to do, I'm going to make little bit changes to this function. That is fun. So what I did, this is my function. And now this function fun will be calling itself. Basically, you can observe over here, I have made a function call to itself. So basically what is happening over here, the function, whatever is the body of this function, there is a line, there is a statement in which the function is calling itself. So that is what it means by recursion. So a simple definition of recursion goes like this. Recursion means a function calling itself. That is the basic definition of recursion. Now, let's say, uh, what is recursion and why do we need recursion? Like basically, what is the use case of recursion? So if I talk about the use case of recursion, for any solution, what we can do, we can write down the iterative approach, right? We can write down the solution using loops, right? And we can also have simultaneously a recursive function, like a recursive solution of it, in which a function is being called simultaneously in order to solve the entire problem. Right? So almost all the problems that can be done using recursion, it is possible that you can write down an iterative approach and vice versa. Okay. So there is a difference between iterative approach and recursive approach. After understanding few more concepts on recursion, I'll be writing down all the differences, like what is the difference between iterative and recursive and when should you go with recursion. Okay. Yeah. So now over here, let's say what I'm going to do. Now, let's say we understood that a recursion means basically a function which is calling itself, right? Now, if we want to write down a recursive function, what are the points that you should keep in mind always, right? So what are the points that you should keep in mind while writing down a recursive function? So the first important point is the base condition. Yes, Vaibhav, exactly. So first one is the base condition, and one more thing, that whenever you make a function call, always call the function, always call the recursive function with a smaller problem. Don't worry, we'll be understanding what does it mean by call the function with a smaller problem, right? So for that, what we'll be doing, we'll be writing down a very small program using recursion, in which what we'll be doing, we'll be simply printing all the numbers from n to 1. Okay, I know that it is a very simple code, and basically we can write down an iterative approach. So the iterative approach basically will be using a for loop in which I'll be using I is equal to n, then I should be greater than or equal to, let's say, 1, and I minus minus, and then basically you can just print the value of n. This is the iterative approach for this one, right? But now I want to write down the recursive approach. So keeping all these 2 points into mind, into consideration, I'll be writing down a recursive approach for this. So let's say I have a function n, and the parameter over here is the value of n. I'm going to print all the numbers from n to 1, right? And now, what is a base condition? So basically, let's say, first of all, if we'll not write down the base condition, what is the problem that will be seen? So let me just open the ID and let's observe what are the issues that we'll be seeing. So, so I'll be writing down a function, and that function will be taking a parameter n. Okay. And I want to just print the values of n, right? So whatever is the value, that is basically inside the function, and I'll be just printing it down. And what I'll be doing, I'll be simply again calling the one with a smaller subproblem. So why is it very much important to always call a function with a smaller subproblem? Because let's say if you already written down the base condition, and I will explain what is the requirement of base condition. So base condition is required basically if you want to end the recursion. At what point the recursion should stop, right? So basically in the iterative approach, we have a condition that if the loop variable is greater than 0, I will just stop the iteration. Like basically if it is lesser than 0, I'll stop the iteration, right? So over here, just like the iterative approach, we'll be having a base condition to stop the recursion. So now over here, I need to print all the numbers from n to so-called 1, right? So I've written down the statement over here that will be just printing it, and I have just called the function with a smaller subproblem. And let's say I'll be taking the input from the user. So the user will be writing down the value of n, and I'll be just calling the function with that. Okay, so now if I run this code, basically I have not written down any base condition. This function will be not knowing that when to stop. Okay, so what kind of error do you think we'll be getting if we don't end the function? Like if we
Stack
don't write down
overflow.
the, yeah, that is stack overflow. So here you might be wondering that we are writing down a recursive function and where this concept of stack comes into picture. So I'll be explaining what is stack and why do we need stack for recursion. So now over here, if I will be adding the base condition, so let's say if n equals to, let's say 0, I'll be just returning from here. And again, if I run this code, you can observe over here. So we can observe that the output has been printed without any kind of error. So basically, when n equals to 0, First of all, the value of n will be 5, then 4, 3, 2, 1. And when the value hits 0, there's an if condition that will not again call the function, but it will be returning it to the caller function. So this is the importance of base condition. And whenever you think about base condition, always think about the smallest problem. Okay. So what was the smallest problem over here? So the smallest problem was that when n hits 0, I don't need to print anything, right? So that is generally considered as your base condition. So in future, if you will be solving more questions on recursion, you will be understanding that how to find out the smallest problem. So one of the approach is basically you just observe the constraints of the question. And if you observe the constraints, let's say the value of n will be given from some lower bound to upper bound, right? Let's say from any, the value of n in the question will be from 1 to 10 to the power 5. So in that condition, if you are decreasing the value of n, then n will be hitting 0 or something like that. So that will become your base condition. So now what is happening over here? Let's say to observe. So the function was something like this. I'll be just copying the same function over here. Okay. So what is happening over here? So let's say this is fun and I have passed the value 5. And the first statement will be executed, right? And then the print statement will be executed, print 5. So 5 will be printed in the output, and then a function call will be made with a smaller value, that is function of 4. Now from here, a new function will be created. A new function will be called with a different value. Again, this value is not equal to 0, so it will be printing 4, and again, it will be calling with 3, that is n minus 1. So in the output, you will be observing 4 over here. Moving on forward. Now again, for fun of 3, a function call will be made. And that will be 3, and 3 will be printed in the output, and the function will be calling for 2. Now again, the same thing will happen. And this process will keep on taking place until the value hits 0. Now again, the same process. So fun of 1, print 1, and then fun of 0. Now over here, when the value hits 0, the base condition, that is if n equals to 0, will be executed, and a return statement will be executed. So now the function will not be calling itself, but it will go back to the parent function. From here, again back to the parent function, again back to the parent function, and so on and so forth till the first function from which it was called. Now from here, it will go back to the main function because this function was called from, so the main function. So basically, we are using the same piece of code, just like the iteration. In an iteration, will be having the body of a loop, right? And that body of the loop will be executed n number of times, and whatever number of times you want it to be executed. The same thing is implemented inside a function. Basically, you will be executing the same piece of code for different values, and that will be helping you to solve the problem. That is basic recursion, right? And hence the output will be printed just like this: 5, 4, 3, 2, and 1. So inside the recursion function, what are the important points that we saw right now? So the first important point is the base condition, right? And after the base condition, we'll be having some of the, let's say, operations that we want to perform, right? And then we'll be again calling the function with smaller problem, with smaller problem. And again, we'll be having some piece of operation. So this is something like, basically, these are the standard things that we'll be seeing in a recursive function, right? So now let's try to observe what are the things like how the recursion keeps its track. So as I mentioned, in recursion, we can see there are the same function is called with different values, right? So now when the return statement hits over here, when the base condition was executed and the return statement was executed, then how will it find out that which function it has go? Like basically, what was the caller function? What is the caller function? There are so many functions. There are 5 different functions with different values. So how will it identify that which is the caller function? Like, what do you think? What is the reason?
It will use stack.
Yes. So it will be using a stack data structure. And why do you think stack is required over here? So if you observe the function call which we did over here, basically always the caller function was right before the current function. If I say this is my current function, then this is the caller function, right? It is right just before fun of two, whichever function was being executed, that becomes basically the caller function over here in this scenario, in this code. Okay, there can be different implementations, but this becomes the caller function right before the current function, whichever function was executed. In this scenario, you can observe it is a caller function. So if I have some kind of data structure in which whatever was the last inserted, that becomes my caller function. That is stack data structure. That is last in, first out. The last function which was called, let's say fun of 5, fun of, let's say 4, and now let's say fun of 3 is being executed. So the last function that was executed, that can be fetched with the help of stack data structure, last in, first out, and hence stack is used to keep the track of the parent functions. So in order to understand the how the data is stored inside the stack and what does the stack store, let's write down a new different like basically a different recursive function so that we can understand what are the values that the stack will be storing, right? For any function, what are the different values required? So I will create one different function. Let me just change these values. So what I'm going to do, I'm just going to write down a function with entry statement and exit statement. So basically they are just statements, let's say, and I'll just print the value of n over here. And similarly, I'll just put the exit statement. So I'm just trying to replicate the standard things of a function, right? So basically here is the base condition, and then I'll be having some of the operations. Then a recursive function is being called, and then again, few of the statements are there. And now what I will be doing, I'll be just running it for n equals to 5. Let's try to observe what will be the output. So can anyone guess what will be the output?
Yeah, so first all entry statements, then the exit statement in reverse order.
Okay, in reverse order. So first of all, for uh, fun of 5 will be called, right? F of 5.
Right.
So
Right.
entry statement for what will be the values of n for the entry statements?
Entry statement 5, 4, 3, 2, 1, and then 1, 2, 3, 4, 5 exit statement.
Okay, yes, exactly. So basically in the output also we can observe, first of all, the entry statements 5 to 1, and then the base condition will be executed for n equals to 0. And then again the exit statement with n equals to 1 takes place, right? So how is this basically working in the background, right? So with the help of recursive stack, we'll be understanding it in a very good manner. So let's say so let me just copy the same piece of code over here, right? So what are the values that will be stored for a function? Okay, so at each and every point, let's say this function is called from what main function, right? And inside the main function, let's say it is called for n equals to 5, and then this function will be executed. So first of all, the main function will be there, right? Now after the main function, this function will be called, that is fun of 5 will be called. This is what we have already written. So this function basically, it will start executing fun of 5. So the first statement will be executed, that is entry statement, that is ES. 5 will be printed in the output. This is my output, okay? So fun of 5 will be executed. This statements, these operations will be conducted, and then the function call will be made for fun of 4, right? So basically you can observe that there was some state of this function, right? This fun of 5 had some state, like basically it had some state. So this operations will, this statement was executed, but this statement is still not executed, right? So the state of the function will be stored inside the so-called stack data structure. So for fun of 5, it will store its state. So what is considered a state? Like basically, what are the things that are present inside a state of a function? So the values of the variables, whatever variables you have declared, all those variables values. Let's say if I talk about the for loop. So if the for loop was executed, then the loop variables will not be required. So it is possible that it is not storing the loop variables, but the function variables, the arguments, the variables that were declared inside the function. So everything will be stored, and the last line where the execution stopped. So the last line which was executed, that was fun of 4. So it will get an idea when the function calls, like basically when the compiler executes this function again, it will get an idea that where to start the execution. So the state of the function will be stored inside the stack. So ES5 will be executed. Now let's quickly see. Then for fun of 4, what will take place? So this statement will be executed, that is entry statement 4, and then the state will be stored. Then again the fun of 3 will be called, an entry statement 3 will be executed. Now again fun of 2, entry statement 2 will be executed, and then again function of 1 will be executed, entry statement 1. Now from here a base condition will be hit for fun of 0, right? And then again it will go back and execute this top function, that is fun of 1. So it will know that where the execution stopped over here, right? So this line is the next line that will be executed. So exit statement will be printed, that is exit statement of 1 will be printed. Then this function will get executed, it will be popped out from this stack. Then fun of 2 will be executed. Over here, the same scenario, exit statement 2 will be printed in the output. Then after executing the entire function, it will again pop the function from this stack. Then fun of 3, same scenario, this will be executed, and exit statement 3 will be printed. Exit statement 4 will be printed then, and exit statement 5 will be printed. So this is how the recursion helps you to get an idea that where you have stopped and where to start the execution, right? Where to resume. So is it clear like how the recursion stack helps you to get an idea? And till now, any doubt, anyone? Just give me a confirmation, yes or no. Okay. So two important things which we saw for recursion, like basically three important things, right? So first was the base condition. Whenever you start writing the recursion, we need the base condition, and always call the function with a smaller value. Okay, so let's try to understand like what is the meaning of it after, like, let's say if you don't call a value, like basically if you don't call a function with a smaller value. So this is the function for printing and all the numbers from n to 1, right? So now over here, instead of calling the function with the same value, instead of calling the function with a smaller subproblem, I will call it with the same value. So what will happen? Currently, fun of 5, let's say it was being executed. Fun of 5 was executed. Now a function call was made to which value? It was calling it to fun of 5. Now again, the function is calling which function? Recursive function with the value 5. So basically, you are just trying to call the recursion with the same problem. For n equals to 5, you are again and again calling. So this also leads you to infinitely executing recursion. So if I run this code, you will be able to observe that we'll get an error of stack overflow. Because here you are calling the function with the same problem. You always try to remember you have to call the function with the smaller subproblem. Okay. So apart from base condition, here is the scenario where you might be ending up in a infinite recursion.
Jay,
Now,
just one question. Like, what is the limit for Stack Overflow there? Like, you are doing recursion, right?
yes.
Without giving the statement, without giving it kind of. Like, what
So
is
it
the limit?
depends. Yeah. So what is the limit of this stack? So basically, it depends upon your system. Okay, so if you want to know what is the limit of basically calling the recursion, all the programming language will be having different sizes occupied, like basically given to the recursion. So if I talk about Python, in that Python you can basically by some import statement you can increase the size of the recursion stack, right? So basically it depends upon your programming language as well.
Oh.
Yeah. So now let's understand one more concept, that is what is a tail recursion. Okay, so we saw the standard way of writing the recursion, right? So first of all, we'll be having the base condition over here, and then we'll be having some operations, like basically some statements that we want the recursion to execute, right? And now we will be calling the function with smaller problem. And now let's say after calling the function, after doing a recursive call, you just end the entire execution of the function. You don't have any further operations that you are supposed to execute. All the operations have been executed. Now the function is being simply called recursively, and then nothing needs to be done. So this kind of function in which the last thing that the function is doing is the so-called recursive call is called a tail recursion. So basically when the function gets back to the running state, let's say currently for fun equals to 5, the function was being executed. Now the function call was made to fun of 4. And now let's say the function call was made to fun of 3. Now if this was the tail recursion, then after executing fun of 3, let's say the next function that will be executed will be fun of 4. So after fun of 4, basically inside the body of the fun of 4, basically we have a tail recursion over here. So after this, we don't have anything to execute, right? Now, none of the operations are remaining. So it becomes very much easier for a compiler to store the tail recursion inside stack. And if you want to understand how basically the compiler reacts to tail recursion, you can read some articles. There will be some articles on GFG as well, that how the tail recursion basically is helpful for the compiler in order to optimize the space. Right? Basically, if you observe over here, if you just pay attention, so I'll give you an idea that how it is beneficial for the compiler, how the space is basically efficiently utilized over here. Now, let's say if we have tail recursion. So what the compiler stores inside the stack, basically at each and every point, it stores the state of the entire so-called function, right? And if the function was a tail recursion, so all these states are not required, right? Because basically whatever state it has stored inside the stack, it is not required. Why not required? What do we have inside a state? We have some variable values. We have some variables, right? And other information will be also there. Like let's say what is the last line that was executed, right? Some different values will be stored. But those are not required. Why not required? Basically, because you don't have any operations to perform at the end, right? So basically you require less amount of space compared to normal recursion. And generally for all the recursive code, somehow it is possible that for some of the questions, like let's say for some of the normal recursion, you might be willing to write down the tail recursion, right? So it will be very much interesting if you try to write down the tail recursion. But yeah, tail recursion optimizes the space that is required. And the compiler, it is very much beneficial for the compiler as well. Okay, so try to read some articles on it. It will be interesting for you guys as well to understand how it is helpful.
Jay, I have a question. So,
Yes.
is there any way to exit the recursion? Exit the recursion code as in for loop, we break the for loop statement and just exit it.
Mm-hmm.
So, is there any way? Yeah.
You want to just stop the execution, right?
Right, and just return to the main function directly instead of getting it into the whole pipeline.
Okay. So the I think if you want to directly break the execution in between, then you might be working with some threads, and inside the thread, you can interrupt the thread, right? So let's say some thread is executing this function. So I have not seen such scenario in which the function basically you can break it in between and stop the execution. So you can divert the execution to some other function, but whatever is present will be executed at the end at some point.
I mean, so let's say this function 5, I reach to function 5, 4, 3, 2, 1. Now, from 1, I don't want to retrace 2, 3, 4, 5. I just wanted to back to main function directly.
You directly want to go to back to main function.
Yes.
Okay.
Would it be possible anywhere?
So yeah, I don't think that would be possible, but I think that might be possible with threads.
Okay.
So you can imagine that let's say one thread was executing the main function, okay?
Mhm.
Right. So it will be having a thread stack, a different thread area, right?
Right.
So let's say the other function is going to basically, let's say this thread invokes or something like that. Basically, it calls a new thread, and this thread is calling a recursion, right? And now let's say somehow, let's say this is a daemon thread or something like that. So somehow, if you stop the execution of this thread, basically you can directly go to the main thread and start executing T1, right? So in a multi-threaded environment, I think that will be possible.
I don't think so because one thread is dependent on second thread, so it will not go into the separate thread mode. If I will talk about the task parallel library, it will eventually go into the same sort of queue like data structure.
So what about both these threads are independent? You start this thread independently, and this thread basically will be calling a recursion. And basically you can stop the execution of a thread, right?
Okay.
At whatever point you want.
Yeah, maybe. Yeah. Thank you. I will try.
Yeah. Okay, so that was all about tail recursion. Now let's try to understand basically what is the difference and like what kind of differences we'll be observing if we have an iterative approach and if we have a recursive approach.
Jay, I have a question here.
Yes.
Yeah, in the above part, you had mentioned the smaller problem, right, in
Yes.
recursive call.
Mm-hmm.
So basically, the smaller problem means uh, the recursive call should lead towards the base condition. Is that correct?
Yeah, base condition is also one of the problem for which you already know the solution.
Mm-hmm.
Yeah, so that will be basically a smaller problem for which you know something that for n equals to 0, answer will be 1. Right? So basically the parent function will be calling to the smaller function. So every time basically you will be calling, you cannot say that it is going to directly to the base condition, but it will be better if you call it that it is going towards a smaller problem for which I already know the answer.
Okay.
Hmm.
Okay, so basically in this example where you were decreasing the n value from 5, 4, 3, if
Mhm.
my base condition would be to exit at the value of 8, then my recursive call would be n plus 1. That would still be a recursive, right? Pause.
Yes.
Okay.
So, yeah, basically smaller problem means first of all, how many values, let's say for n equals to, let's say you have the value 5, right? So you are targeting on printing all the numbers from 5, let's say 5, 6, 7, and 8. This was your target, right? So fun of 5 means you are going to print this many numbers. Now, what does it mean by fun of 6? It means that you have to print 6, 7, and 8. This becomes a smaller problem in which you are printing all the numbers from 6 to 8. This problem means 5 to 8. Right?
Okay.
So in general, you can call this is printing n to 8. This is printing n plus 1 to 8. So this is a smaller problem compared to this. Right? So in terms of increment and decrement, don't take it in terms of increment and decrement. Take it in terms of the task that function will be doing. It will be doing less amount of task.
Okay, yeah, got it. Thank you.
Okay. Okay, so we were talking about what are the differences between iterative approach and recursive approach. So as I mentioned that you can write down the same iterative approach using a recursive approach as well, right? So how is this recursion helpful? Like what are the benefits, or let's say like what is the benefit of iterative approach compared to recursion, right? So in the iterative approach, what do we have, right? How the function is like basically how the iterative approach gets executed. We'll be having loop, right? And that loop will be executing some set of statements simultaneously. Right? And over here, what this recursion will be doing? So recursion will also be doing the same kind of thing. Right? So what do you think, like, how is recursion helpful? And yeah, any ideas?
Yeah, if we want to persist the state of any then the recursion helpful.
Sorry, process the
Yeah, if we want to persist the state, maintain
persist
the
the
state,
state. Okay.
then only recursion would be helpful.
Yes. Okay.
In the hierarchical mode, when we don't know means how deep the hierarchy is, in that scenario, recursion is helpful. It's a kind of dynamic approach, but loop, it's finite, I believe. Suppose if there is parent child and you don't know how many deep the child hierarchy is, in that scenario, recursion is helpful. And loops will use the less space because
Then yesterday, 2 times I made, you did not eat. Just for the sake of.
Yeah. So basically, yes. So one answer we got, that is if we want to persist this state, right? And that is basically, and one more, I think it's a trade-off between readability and heap space. Okay, yes. So I would like to address one thing that the loop cannot do, basically. Like uh, let's say loop can also do, you can execute, write down the same thing using loops as well. But the first thing is readability. Everyone who wrote down that the readability of the code becomes easier with recursion. That's absolutely correct. Right? Now let's say if I try to explain, let's say here you have a function f1, or let's say, yeah, let's call it as f1, and you have some value of f1, and this function is a recursive function, right? And let's say it is calling f1 is calling to, let's say, with a smaller problem. And inside this f1, what I am having, one more thing, I will be having, let's say, one more function, let's say that is fun, or let's say f2. And this f2 will be called with n, and this f2 is also a recursive function. And basically what this function will be doing, f2 will be, let's say, finding out the factorial or something like that. So that would be n into something like that. Okay, Harshad. Yes, exactly. So Harshad is saying that basically the readability of the code becomes much simpler with recursion. Yes, exactly. So over here, the other thing apart from readability is that, let's say if I want to divert the flow, and and let's say for n equals to, let's say 5 for some value of n, I want to do some extra things. I want to let's say print a statement 5 number of times. Let's say I want to print GFG 5 times. Okay, I want to print GFG 5 times, and for n equals to, let's say 3, or let's say for n equals to 4, I want to do the same thing. I want to print GFG 5 times. For n equals to 3, I want to print GFG 5 times. And I'm writing down this decrement of the values. And over here, for each an individual value of n, I want to print a different statement. Let's say hello. So first of all, for n equals to 5, hello will be printed, and then 5 times GFG will be printed. And again, hello. Then again 4 times GFG, or let's say 5 times GFG. Then again hello for n equals to 3, and then again 5 times GFG. So you can write down the logic. This logic can be written with iterative, but you will be having so many nested for loops. Okay, so we will be having first of all one for loop that will be starting from I equals to 0, let's say from I equals to 5 to I is greater than or equal to 1. So this for loop, hello will be printed. And again, what I will be doing, I will be having one more for loop, I is equal to, let's say, so-called j over here, right? So j is equal to 0 to, let's say, j is equal lesser than 5. And over here, I will be writing down GFG. Okay. And again, let's say for each and every value of j, I want to print something. For each and every value of j, I want to print, let's say, k is equal to 0 to k is lesser than, let's say, 5. I want to print so-called world, something like that, right? So you can observe over here, there are so many nested for loops available, right? And when you work with nested for loop, and if you have written like solved the questions, many questions using for loop and nested for loop, you might have observed that it's very much difficult for you to understand what this loop is exactly doing. Because over here, everything is revolving around so-called loop variables. So you have to observe the loop variable and understand how many times it will be iterated, right? And inside the loop variable, if you have one more for loop, you need to understand for what values this loop will be executed. So when the discussion around iterative approach comes, nested for loop or nested loop creates confusion, right? And if you write down the same thing, if you write down the same thing using recursion, what you have one statement to print hello. So I'm just writing down the syntax. So one statement for printing the hello, this is n. And now after printing the hello, let's say I have one more function that is fun1. This will be called, and this fun1, it will be basically printing GFG. Let's say GFG. And this fun1 again will be calling recursion in this manner, right? And individually, let's say if you want to call this piece of code, if you want to individually call this function fun1 with some other requirements, then you can use this piece of code again and again, right? So whatever benefits you have with methods, whatever benefits you have with writing a function, all those benefits you have with recursion as well, right? So if anyone says like, why do we need recursion? So basically, we can answer the question like, if we want to use a function, like basically we want to execute any piece of code from anywhere, from any part of the code, we write down that inside a function, right? And the same benefit applies for recursion as well, because it is basically a function, right? So what I'm trying to say is that inside this for loop, inside this nested for loop, if I want to call this for loop, if I want to execute this piece of code from any part of the code, then I cannot do that, right? I need to write down this again and again. So with the help of recursion, if you have written down in this manner, you can call this function from whatever part of the code you want, right? So code reusability is also one of the benefit of recursion, right? And readability is also one of the benefit of recursion. So what are the downsides of recursion? Anyone? Okay, space, execution time, extra heap space is required, okay? So yeah, so one of the disadvantage of recursion is that whatever code you write down using iterative approach, you don't need to use any extra space in order to execute that iteration, right? If you want to execute any kind of for loop, you don't need any extra space inside the memory. While in case of iteration, space is managed by us only. Yeah. So over here, basically, whenever you create, or let's say, see the recursive stack which I have shown over here, no? So you might be wondering that, okay, whenever I'm going to use a recursion, at that time only I will be like the compiler will be utilizing the so-called recursive stack. No, that is not the scenario. Let's say I have the main method. I have the main method, and inside the main method, I am calling a function. Okay, and this is my function that is being called. And this is not recursion. Okay, so a simple call to the function and some operations are there over here that will be executed by this function, and then whatever is present inside the main function that will be executed over here. So now if main is executed, so main will be present inside the stack. So main method with its state will be present, and then it is doing a call to function. Right? So it is making a call to the function. So fun will also be stored inside the stack. Okay. So not only recursion, but general calling of function also uses a stack data structure. So the downside of using recursion is basically you will be using more space. You will be using more space, and due to that, whenever you write down a recursive code, the auxiliary space is never constant. Right? If you just ignore the recursion stack, then and only then you can call it as a constant space according to your approach. But the space is not constant whenever you write down a recursive approach, because in the background, recursion is going to use recursive stack, and that is the reason. So sometimes it is possible that the iterative approach, when you will be studying out dynamic programming, at that time, what will happen over here? So whenever you will be studying the dynamic programming, so over there as well, you will be having iterative approach. Basically, you will be having an approach using tabulation format. Like basically, you will be using loops to write down the solution, and you will be having memoized solution that is using recursion. Okay, so repeat the point on space. So whenever I was saying that whenever you write down the recursive approach, the space complexity can never be considered as constant because recursion uses recursive stack, right? So how many functions were called again and again? What was the maximum time a function was called? Like how many functions were called or how much space was occupied? That becomes the space complexity. And apart from that, whatever logic you are using, right? So constant space and recursion do not go together for any solution. Yeah. So I was talking about dynamic programming. So let's say, so what are the downsides of using a recursive approach? So if you talk about dynamic programming, over there, you will be having a solution using recursion. Okay. So till now, we have not covered dynamic programming. So just think that we have a recursive solution and we have an iterative solution as well. Okay. So most of the time, recursive solution will be working. It will be logically correct. Everything will be correct. But depending upon the constraints, depending upon the value of and whatever is the value of the input array or anything, it is possible that you might end up getting an error of stack overflow or something like that, or time limit exceeded. Okay, so time limit exceeded you will be getting because some of the compiler, let's say if the stack has overflowed, like basically you don't have enough space, and the amount of time that was given to the solution, given to the code execution, if it expires, it prints time limit exceeded, although in the background, your recursion might have given an error of stack overflow. Okay. So over there at that time, you can see that downside of recursion is basically you will be getting stack overflow in some of the questions. Like mostly it is working, all the iterative approach will work, then simultaneously recursive approach will also work. Okay.
Jay, will it have a same time complexity as iterative approach and like it is impacting the space, right? And
Yes, it is
will it impact,
impacting the space.
will it impact the time complexity also?
So if you ignore the operations that are performed, like let's say stack, push and pop, basically they are constant, right? So the time complexity will be same in that scenario as well. Okay. But the space will be impacted.
Okay.
So if you have any kind of doubt, like basically if you till now everything was clear to you guys, then just give me a confirmation, yes or no, in the chat box. So we can move ahead and understand basically the other concepts as well. Okay, fine. And the audience who is currently watching us live on YouTube, you can also write down your doubts in the chat box as well. Whatever confusion you have, I will be answering to your questions as well. Okay. So yeah, so let's start and let's go with the time and complexity, time and space complexity. Basically, how to find out the time and space complexity. So let's say I have a code. I am just going to, let's say, write down a code for a recursive code for just finding the factorial of a number, let's say. Okay, so let's say so what I will be doing, I just want to find out the factorial of n. So I will be multiplying the value of n with a smaller problem, that is fun of n minus 1. Right? And whatever is the value of this multiplication, I will be just returning it. And what do you think will be my base condition over here? Recursion to find out the factorial. What do you
n
think will
equal
be the
to
base condition?
equal to 0.
Yeah, if n equals to 0, or let's say if n equals to 1, I will be returning. So it also makes sense that if you write down n equals to 0, then you can return 1. But you need to understand that is there any problem for, like, basically, do you have a problem? Let's say, what are the constraints of n? And generally for finding factorial, you don't find out the factorial of 0, right? You find out the factorial of 1, the smallest number. So whatever is the smallest problem for which you already know the answer, I'll be writing down as my base condition. So this is my function for finding the factorial, and I can call this function with, let's say, 5, and it will be returning me some value. So let's say so the return type of this is going to be n, basically integer, and we got the factorial of 5 as 120, right? So what is happening over here? So one question to everyone, like as we discussed that what is a tail recursion? We understood what is a tail recursion. So what do you think this function which I have written over here, for everyone who is watching us on YouTube as well, and for the students of our class, what do you think, is this a tail recursion? Because I think it is a tail recursion. Like, I want your views. What do you think? Because the last thing that this function is doing is calling the recursion function, right? So what do you think? I think it is a tail recursion. Do you guys agree? Okay, so Shubham says yes. Okay, Vipin says no. Okay, no, it needs to store the value. Okay, Satish says yes. So Satish, like, can you unmute and let's say, can you explain why do you think it is a tail recursion?
Yeah, so this function is called every time, right?
Hmm.
It creates a chain, that's why they thought it's a tail.
Okay. Okay. So if we try to observe what this function is doing, basically, you can observe that, let's say if I'm going to find the answer for fun of, let's say 3. So what will happen over here? So it will check the base condition, n equals to 1. It is not equal to 1. So fun of 2 will be executed, right? And then fun of 2 will be called. Again, base condition 2 into fun of 1, because the answer depends upon fun of n minus 1. And then from here, it will be making a function called to fun of 1. And now it will be returning, the base condition will be executed and it will be returning 1. So this was one of the state, right? This function was executed. This function was executed. So if you focus on the definition of tail recursion, I explained that the last thing that the function will do is make a recursive function call. So fun of 1 was executed, it will be returning 1. So that value will be returned over here, and fun of 1 will be returning me basically 1. So this fun of 2, if this was a tail recursion, then it was not supposed to do anything else. Okay, after the recursive function call, it was not supposed to do anything else. But over here, what this function will do, it will multiply 2 with 1. This is an operation. It will multiply the value of 2 with 1. And then it will then it will return the value with the help of return statement to this function. So in tail recursion, directly it will, after calling the function, after doing a recursive call, it will go back to the parent function. No operation will be performed. Okay, so this is not a tail recursion because some operations are performed after the execution is resumed, right? So this is basically how this factorial of n is executing, the recursive approach. So how to find out the time complexity of it? So let's say, so for that we need to understand that if I have the value of n, fun of n, so what do we need? What do I need in order to calculate the fun of n? I need the value of n and I will be multiplying with fun of n minus 1. So if I want to find the value of fun of n minus 1, what I will be doing? I will be needing the value of n minus 1 and I need the answer for fun of n minus 2. And for fun of n minus 2, what I will be doing? I will be needing the answer. So I will be calling fun of n minus 3 and so on and so forth. So what do you think? What will be the last function call? So the last function call will be something like this. So if I need the answer for fun of 2, it will be 2 into fun of 1. And what is the answer for fun of 1? At the end, you will be ending up at a base condition. So fun of 1 is what? Equal to 1. Right? So if I want to know what is the time complexity of executing a function, let's say I want to find out t of n. So t of n is what? It is nothing but t of n minus 1 and some operations that I'm doing. So what are the operations that you are doing? So inside this static function, one operation that will be done each and every time, that is this condition will be checked. Constant operation. I'm taking the other operations like multiplication, addition, if condition, condition checking as constant operation. Printing out anything in the output, that is a constant operation. And over here, some multiplication will be done each and every time. One multiplication of n with whatever value is returned, that will be done. So an extra addition work of 2 unit is done, just taking it as 2 operations. Okay, so 2 operations are done. Right? So if I write down t of n minus 1, so that would be t of n minus 2 plus some extra operations. That is 2 operations are defined. So t of n minus 2, that is t of n minus 3 plus some extra operations. And so on and so forth. And for t of, let's say 2, I know that it will be getting the answer of t of 1 and some extra operation. And for t of 1, I know how many operations are basically done. It will do only 2 operations. Why 2 operations? Basically, first of all, the condition will be satisfied, checking the condition, and then the return statement, one more, right? Or you can consider it as a single statement. Let's not consider the return as an operation. So only one operation will be done. So if you want to find out that what is the time complexity, like let's say what is the number of operations that are performed, you need to count how many times the function was called. So I can see how many times the function was called. What is the total count? It is from 1 to n. You can consider it as n plus 1 times, right? So if the value is n, then the recursion is directly proportional to whatever is the input value, right? So the overall time complexity of this approach comes out to be order of n. That is how many times the function is being called. I can see n number of times in the worst case scenario, in order to find out the answer. So the time complexity of this solution comes out to be order of n, right? And what is the other thing? So in order to simplify this, what I can do over here, in order to simplify this and how to reach to a specific value, which I have written over here. So what I will be doing, I will try to substitute this value. T of 1 will be substituted over here. That is 1 plus 2. Okay. So I will just keep this 1 aside and I will keep on adding the value. Okay. So T of 2, that will be what? 1 plus 2. Okay. So I will keep this 1 aside and I will say that T of 2 is also doing one operation, that is 2. Like it has only got 2 operations to do. So that value will be returned over here to something, right? So let's say over here you have T of 3 is nothing but T of 2 plus 2. So replacing this by 1 plus 2, that would be 1 plus 2 plus 2. And again, let's say over here you have T of 4. T of 4 is nothing but T of 3 plus 2. So this is what? T of 3 is 1 plus 2 plus 2, this many operations. So replacing this value in place of T of 3, what I will be getting? I will be getting 1 plus 2 plus 2 plus 2. So over here, you will keep on adding 2 each and every time. So how many times do you think this value 2 will be added? N number of times. Why n number of times? You can observe here only one operation was performed. Here 2 operations. If I ignore 1, 2 operations, then 2 operation, 2 operation. Right? So from T of 2 to T of n, how many values are there? This. What is the number of values over here?
N minus 2.
Okay. So over here, this is, let's say if this is T of 2 and this is T of, let's say 5. So how many values? 2, 3, 4, and 5. So that is 5 minus 2 plus 1. That comes out to be 3 plus 1. That is 4. Right? So that is n minus 2 plus 1. Or let's say you can call it as n minus 1. This many values are there. Right? So n minus 1. So basically, for each and every t, you know that 2 operations are performed. So 1 plus what you will be doing, you will be keeping on adding 2 how many times? N minus 1 number of times. And for writing the big O notation, we have seen that what should we ignore? We should ignore the constant terms. So this 2 will be ignored, right? Constant terms are ignored and the non-significant terms are ignored. So this is also ignored, and n minus 1 and n, what do you think will be will be the difference, right? It will not make much difference if I subtract 1 from it, right? So the overall time complexity over here comes out to be order of n. So is this clear?
One doubt. So uh, for recursive, usually it will be put to the power n, something like that, right?
No, that is not the scenario. It will not be exponential every time.
Okay.
So what about the space? How to analyze that? What amount of space will be occupied, right? So we need to understand. For that, we need to visualize the stack, right? We need to visualize this stack. So what do you think? What is the amount of space that will be occupied by stack? So over here, you need to, if you want to get an idea what is the auxiliary space that this recursion is using, what you can do, you can draw the recursion tree. So what does it mean by a recursion tree? So recursion tree is nothing but just align the function calling. That is, let's say first of all, fun of n is called, then what you are calling fun of n minus 1, then you are calling fun of n minus 2, then you are calling what? You are calling fun of n minus 3, and so on and so forth till fun of 1, right? So what do you think in recursion stack, what are we storing? At each and every point, we'll be storing the state of the function. So these functions will be stored, right? All these functions will be stored. So how many functions are there? How many functions are there? N, n minus 1, n minus 2, n minus 3, and 1. So that comes out to be n functions are there in total. So this many function calls and their state will be stored inside the recursive stack. So the recursion stack will be occupying the space equivalent to n in the worst case scenario. Right? So here fun of n will be there. Fun of n minus 1 will be there till fun of 1. Right? So this is total n number of times. So the space complexity in this scenario comes out to be order of n. Okay. So is it always order of n? Right? It is also possible that some of the functions you might have written, let's say the recursive function in which you will be finding out the Fibonacci, right? Fibonacci of n will be coming to that function. So over here, you will be having a recursive call, basically will be done twice. Like basically, you'll be calling for n minus 1 and you will be making a function call to n minus 2. Right? So for each and every Fibonacci n, you will be making two different function calls, right? That is fib of n minus 1 and fib of n minus 2. So over here, how to identify? Basically, if I draw the recursion tree of this Fibonacci recursion, you can observe that tree is basically spread it out, right? It is not linear. It is not a skewed binary tree, like not a skewed tree. So in this scenario, what you need to find out, and let's say for fib of n minus 1, you will be making a call to fib of n minus 2, and you will be making a call to fib of n minus 3. And for this, you will be making a function called to fib of n minus 3 and fib of n minus 4. So how to identify that? What is the stack size in the worst case scenario? Can anyone guess how to basically identify this kind of recursion?
You mean for the space complexity or time complexity?
Space complexity.
Okay.
Okay. Two to the power n leaf nodes. Assuming that the longest depth of recursion tree as the tree height. Yes, Yochan Chandesh. Yes, exactly. So if we talk about the space complexity in terms of recursion, no. So over there, basically, what I mentioned that at any instant, like basically I said that in the worst case scenario, what is the size of the stack? Like how many function calls will be stored? So in the previous one, so just let me reshare my screen just a minute. So basically, in order to identify that what is the amount of space required, right? So what is the recursive stack? Like how much function calls are going to be there, right? In the recursive stack. If you want to identify that thing. So you need to understand that in the worst case scenario, how much will this stack will be filled? Like basically in the worst case scenario, what is the worst case scenario that how many in the worst case scenario, how many times the function will be calling it itself. So in the worst case scenario, if you observe this Fibonacci recursion, so that would be fib of n minus 2, and this is fib of n minus 3, right? And fib of n minus fib of n minus 3 and fib of n minus 4. So in the worst case scenario, the height of this tree is the worst case scenario, and that many times, whatever is the height of this tree, that many times your in the size of the stack will be occupied. So you need to find out the height of the tree in that scenario. That what will be the worst case scenario of that the recursive stack will be filled. So don't always take in this manner that how many times the function is being called. How many times the function is called is not equivalent to the auxiliary space that will be occupied by recursive stack. It is equivalent to, in worst case scenario, what is the height of this recursive tree. That is going to be the auxiliary space, not how many times the function is called. Okay, that is completely different thing. How many times the function is called, it is possible the function is called more times compared to the recursive stack. Okay, so let me just summarize. Let me write down what is space complexity over here. In worst case, what is the size occupied by recursive stack? That is your space complexity. So the recursive stack, why this is the scenario? Like, it's very simple to understand. What does it mean that in the worst case scenario, what is the size of the recursive stack? So it means that that anything will be present inside the recursive stack if it was called, right? So if fun of n was called, then it is present inside the recursive stack. If fun of n minus was called, n minus 1 was called, then it will be present inside the recursive stack. If n minus, let's say, 2 was called, then and only then it will be present, right? So future orders, let's say fun of 2 was called, and now let's say fun of 2 was done with the execution, then it will not be present. And in next scenario, let's say if fun of n minus, let's say, 3 was called, and then fun of n minus so-called 4 was called, right? So the fun of n minus 2, which was already executed, is not contributing to the space that is occupied by recursive stack, because it is not currently present inside the recursive stack. So the functions that are already executed does not let's say increase or pay any kind of importance in finding out the auxiliary space. But in worst case scenario, at any instant, in the worst case instant, how many functions are present, that is the space complexity. Okay, I hope everyone is clear with the space complexity of recursion.
The statement you said, n minus 2 column wouldn't be contributed. Can you please repeat that?
Okay, so I will draw two different state of the recursion stack. This both are same recursion stack 1. Okay, this both are the same recursion stack. So let's say in this recursion stack, at this instant, at some instant, this many function calls are present. Okay, and at some instant, the same recursive stack is having size equivalent to, let's say, this, and earlier it had size equivalent to this. Let's say over here, what is the size? 2, and now what is the size over here? Sorry, it is 3 and 4, right? So this is 3 and 4, the size of the recursion stack. Okay, so if this fun of 2 was already executed, right? If it was executed, then it will not be present inside the recursion stack. So that is what I am trying to say. So if fun of 2 was executed, then this fun of 3, fun of 4 basically are not going to be above fun of 2. In the recursion stack, if let's say this has done with the execution, it will not remain inside the stack, right? It will be popped out from this stack, and whatever functions are left for complete execution, they will be only present inside this stack. So in these two different states over here, this is state 1 and state 2. From among all the states of the recursion stack, in the worst case, what do you think is the space occupied by recursion stack? That is the space complexity. So in this state, I can see only 3 elements are present, but in the state number 2, I can see 4 elements are present. Okay. So to generalize it in, let's say over here, n minus, let's say 2 elements are present just for simplicity, or let's say n minus x elements are present inside this stack, and over here, n minus y elements are present. Okay. And the value of n minus y is basically, let's say, is greater than n minus x. So this becomes your auxiliary space and not this. Okay. So at any instant, in worst case scenario, whatever is the number of functions present, that is your space complexity.
I have a doubt. So in Fibonacci series, we call two methods in a single line. So the space will be in same box. We'll have two functions mentioned, right? Am I correct?
Yes, we have two functions mentioned over here. Yeah.
No, in stack diagram. Are we going to represent like that, or how is it?
No, we are not going to represent in that manner. Because at any instant, only one function will be executed, not simultaneously two functions are executed.
Okay.
Yeah. So at any point, only one function will be executed. So over here, let's say from fib of n, the control goes to, let's say a function call was made to fib of n minus 1. So this will be executed now. At that time, although inside fib of n minus 2 was supposed to be called, but this is not currently being executed. Only this is being executed. And then let's say this was the next function that will be executed. So in this manner, execution takes place, not simultaneously.
Fib of n minus 3, what is the order when it will
When it will be
inside the stack,
executed.
when it will be how it will be arranged inside the stack?
Fib of n minus 3. So let's say currently, let's say fib of n minus 2 is being executed, and now its execution is stopped. So the next line contained fib of n minus 3. So the function call will be made to fib of n minus 3. So in this stack, so let's say if it was something like this, fib of n minus 1, and then fib of n minus 2. Now this function was executed, fib of n minus 2. So it will be removed from this stack. And now, if this was supposed to be called from fib of n minus 1, so fib of n minus 3 will be pushed inside this stack.
Okay. Got it.
Yeah. So as we are discussing about Fibonacci series and like how to write down the recursion using Fibonacci. So let me just go through that question, that what is Fibonacci series, and like that is also one of the important question of recursion as well. Okay, and it goes till dynamic programming as well. So many concepts can be explained with Fibonacci. Okay, so Fibonacci series goes something like this. So if I say the first element is 1, so 1, 1, and it will be having 2, 3, 5, 8, and so on and so forth. Okay, so basically the current element is the sum of previous two elements. So 1 is 0 plus 1, and this 2 is 1 plus 1 in this manner, right? So we can have a recursive function for Fibonacci. So let's say if I want to find out Fibonacci of n, then what values do I need? I need n minus 1 value, and I need the value at n minus 2th position in the Fibonacci series. So let's say that function call will be done for fib of n minus 1 and fib of n minus 2. So what about these values? What I am supposed to do with these values? You are supposed to add this value in order to get fib of n, right? And now what about the smallest problem? So whenever it comes around finding the base condition, think about the smallest problem for which you already know the solution. So what is the smallest problem for which I already know the solution over here?
0 and 1.
Sorry?
0 and 1.
0 and 1. Yes. And if I try to ignore this 0, I can say that if the value of, let's say, fib of 1, or let's say if it is fib of 2, I know the answer is going to be always 1. This is first element, this second element. If I ignore this, I know the first and the second element are always going to be 1. So that is going to be our base condition over here. The smallest problem, we already know the answer. So Rohit is saying that while solving problems using recursively, are you able to think of each step that will take place? Okay, yeah. So yes, we need to think about the upcoming steps in order to write down a recursive approach. So you need to understand for what state, like from what state I need to find the answer. So you need to think in future as well. Like for this problem, I'm calling the function, then this will be the state. And for a smaller problem, what will be the state of that function? Okay, so yeah, let's go back to this Fibonacci. So if I write down the recursion, so that would be the base condition will be, let's say, if n equals to so-called 1, or let's say if n equals to 2, I will be returning 1. And this will be fib of n minus 1 plus Fibonacci of n minus 2. And whatever is the value that I will be returning. So this is my Fibonacci, right? So let's try to observe the recursive so-called tree of it, that how the recursive tree will look like. So first of all, let me just code this so that we can find out some answers and see how the code is basically giving the answer. Is it working perfectly fine or not, right? So I'll call this at fib, and this will be my Fibonacci. So the base condition is that if n equals to 1 or if n equals to 2, I will be returning 1 in this scenario. And for finding fib of n, I need fib of n minus 1. And what else I need? I need fib of n minus 2. The two values are required, right? And now let's call it for fifth Fibonacci number. So according to the series, what will be the fifth Fibonacci number? It will be 5. So we got 5, right? So this function is working perfectly fine. So let's try to visualize the recursive tree of it. So I will find the answer for fib of 5. That is the perfect value which I think that will give us an idea, right? So let's say it is fib of 5. So simultaneously we'll observe this function as well. So I'll be calling fib of n minus 1 and fib of n minus 2. So first of all, fib of n minus 1 is called, and then after this is executed, then this function will be called and the value will be found, and then the operation addition will be done. Right? So fib of 5, a function called to Fibonacci of 4 will be done, and a function called to Fibonacci afterwards. Okay, so let's go with the flow in how the functions will be called. So then fib of 3 will be called, and then what will be called? Fib of 2 will be called. So on calling Fibonacci of 2, the base condition hits down, right? And fib of 3 will be calling which two functions? It will be calling fib of 2 and Fibonacci of 1. Right? So after executing both of them, fib of 3 has done the execution. It will add the values, and then fib of 4, basically it was supposed to execute this Fibonacci of 3, and then it will call Fibonacci of 2. And now after finding the value, this is again the base condition. So the addition of these two values will be done. Addition will be done. And then we have the answer for Fibonacci of 4. So I need to get the answer of Fibonacci of 3 again, right? Because to find Fibonacci of 5, I have got Fibonacci of 4, but I need Fibonacci of 3 as well. So this function will be executed. Now here, from here, again, what will be executed? Again, a function called to Fibonacci of 2. First of all, it will be done. It is a base condition, so we got this value. Now again, what will be done? Again, a function called to Fib of 1 will be done because we need the answer for Fibonacci of 3. It is the base condition. An addition will be performed. After getting the addition, I have the answer for Fibonacci of 3. So I have Fibonacci of 4 and I have Fibonacci of 3. So finally, both the values will be added and then I will be getting Fibonacci of 5. So in this manner, the recursion takes place. So ultimately, at each and every point, you might have observed one function was only being executed, no simultaneously. Although you can observe two functions are called, right? So not both of them will be executed at the same time. First of all, get the value of this and then get the value of this and add both of them, because the addition operation can only be done after getting both the values.
Like,
So this is
like if it, so you're saying like whichever returning the value, I mean, whichever it is,
whichever, sorry.
then, I mean, the value which is going to 2 and 1, so that will be returning the value first, right? And it will be returning to fib of 3 first. I mean, the left side of the fib of 3 will not be executed.
I missed you from fib of, like you said that two values for 2 and 1. I missed that part.
I mean, right side of those statements. I mean, so you said like that is returning first, right? I mean, it is going to 2 and 1, and it will return 1.
Hmm.
So, and the leftmost value, you said like it will not be executed, the fib of 3. Am I
It will
correct?
not be executed.
I mean, you said the fib of 3 value is already, we have found it. So you said this statement will not be executed again. I mean, this function.
No,
That was
I said over here in this part, are you mentioning this part? That when after getting fib of 4, did I say that fib of 3 is already found? So are you saying this thing or like?
yeah.
No, I did not mention that we have already found fib of 3. So again, the value will be calculated.
Okay. Okay.
Hmm. So the concept which you have addressed over here, basically, you can observe, see, just giving you a short idea that in what different areas like this recursion is used. So iteration, if you see, no, this iteration, like let's say the iterative approach, or let's say nested for loop or nested loops, right? So they don't particularly hold, like let's say it is not a specific concept. Iterative approach is a paradigm of writing a solution. Similarly, recursion is a paradigm of writing a solution. Okay, it is not any technique that is going to solve the so-called problem very quickly or something like that. It is not a technique that will impact the time and space complex. It will not improve the space complexity or improve the time complexity. It completely depends upon the logic which you have written. Okay, so if I talk about stack, basically it will help you to get the topmost last in first out in order of 1 time, push and pop in order of 1. If I talk about heap, it will help you to get the smallest or largest in order of 1. Right? If I talk about merge sort, that is an algorithm that will give you the array in sorted manner. It is solving something. It is in itself, it is a solution, but recursion in itself is not a solution. It is a way of writing a solution. Okay. So what I was trying to say, this concept that is recursion, if you observe that, just a simple idea about what is dynamic programming. So if you observe over here, fib of 3, right? In this point, at this point, you have already found the answer for Fibonacci of 3. And if you observe over here, you are again trying to call the Fibonacci of 3 and finding the answer. So that is something that is redundant, right? Some tasks are being repeatedly done, although it is not required, because somehow, let's say if I stored, let's say in some variable or somewhere, I have stored the value of fib of 3. It was, let's say it is equivalent to 2. I have stored this value. So instead of making a function call and instead of doing the same thing again and again, I should directly go and look inside this variable and get the value, right? So that is what dynamic programming does. Okay. So all the function calls which are already done, it will store some answer. It will store its answer. So you might be wondering where the answer will be stored. It will be stored inside some 2D array or something like that, or a 1D array. And it will look into the 1D array for some specific values. And if that value is present, it will avoid making a function call. That is what it means by dynamic programming. And specifically, it is memoization. Just memorize the solution for some functions, for some problems.
So, do we need to write a special function for that, or JVM or any technology runtime makes that operation
Uh,
dynamic?
this part, like how will we store it inside some?
Yeah. Do
So
we
for
need,
yeah,
or
yes.
just JVM take care of it?
No, you have to do it logically. So there will be logical steps of doing it. Okay, so let's say I will map some of the cell. Let's say if I want to store fib of n, I will say that inside this array, which I will be calling as DP array. So it will identify that which is the row number and which is the column number for fib of n. Okay, so this, how to identify which cell number, I will explain when I will be talking about dynamic programming, but this will be done logically. It will be completely on your hand how you want to implement it.
Okay.
So yeah, this is what it means by recursion and an introduction, like basically dynamic programming, right? So dynamic programming heavily uses recursion. If you are very much good at writing down recursive code, if you are very much good at understanding that how the recursion is taking place, then dynamic programming is going to be very much easy, because the flow of finding the solution, the most optimal way, that is iterative in dynamic programming, starts from recursion, basic recursion solution, then you memorize it, and then you find an iterative approach by just converting the recursion into iterative approach. Okay. So recursion is very much important if you want to master dynamic programming. So right from this point, I'm just giving you an idea. Practice recursion a lot. If you don't have any practice, or if you have like lost some touch with recursion, so start doing it right away, and from this session itself. Okay. And so whenever you will be studying dynamic programming, I will be focusing more on recursion part. So at that time, you will be able to understand. Okay, so recursion is, if you are able to understand recursion, then I don't think dynamic programming is that much difficult. So yeah. So let's jump into solving few of the questions, and let's try to get our hands on writing down the solution. So we'll be seeing a very simple question, for now, for the first question, that is sum of digits, right? So I know the iterative approach will be there, right? So after discussing iterative, I want you guys to give me an idea that what is the recursive approach of it. That is sum of digits.
Yep, just like we write the factorial part, we can write, you know,
Mhm.
n plus f of n minus 1, and that could do the sum, right?
Sum of the digits. Okay.
But if n equal to 1, then return. I mean, at last we need to return 1 plus f of n minus 1.
Last we have to return
1 plus f of n minus 1. I mean, that will take each and every digit. I mean, it will sum each and every digit.
So can you just give me an idea about how the recursion will look like? So basically, if I want to find out the sum of digits of n, so how can I basically, what will be my next function call for this? Like recursively, what value should it call?
Yeah, it will first go to the n minus 1 till the 1.
N minus 1, sorry.
Yeah, n
But
minus 1. Like if it is reaches if n reaches to 1, it will return 1.
So you are saying that to find the answer of a function of n, I have to make a function called to n minus 1. Is it so?
Yeah, I guess.
Okay.
We
I
can
mean,
use the
1 plus f of n minus 1.
Sorry. Again, please repeat it. Okay, so Rohit says f of n minus 1 plus f of n minus 2 and f of 1 equals to 1. Okay, so first of all, we need to understand how to find out the solution, basically how to find out the sum of the digits. So the question says for any number, let's say if n equals to 12, I am supposed to find out, let's say for n equals to 12, I need to find out the sum of the digits. So output for this comes out to be 3. For let's say n equals to 1 to 9, so the output will be 12 because 9 plus 2 plus 1, that gives me 12. 1 plus 2 plus 9. And this gives me 1 plus 2 equals to 3, right? Sum of the digits. So we need to identify, let's say if I want to get the answer, of addition of let's say 1, 2, 3, 9 and 7, a big number like this. If this is my number and I want to find out the sum of digits of it, so what I need to do, if I get a digit, let's say 9, and I need to find the sum of this, that is 7, 1, 2 and 3. And in order to get the answer for let's say 7, 1, 2 and 3, what I need to do, I can extract the last digit and I have to find out the sum of digits of 712. For 712, I need to find out the sum of 71, sum of digits of 71, and I will add 2 to it, right? And for 71, I have to find out the sum of digits of 7 and I will add 1 to it. And for 7, I know it is a single number, right? So I will be returning 7 as it is. So the sum of it will be 7 itself. So over here, what I can observe, first of all, if this is my number, see, the problem over here is that this is not a string, right? It is an integer value. If it was a string, then I can directly get the last character, right? So if I talk about an integer value, so can anyone say how to find out the last number, how to find out the last digit of an integer? If I want to extract 9 from 7, 1, 2, 3, what will be my process? Mode, okay, and modulo 10. Gajanan says if n divided by 10 equals to 0. Yes, exactly, Gajanan, okay. And yeah, sum of. So Himani, n minus 1 instead of n, no. Why are we subtracting 1 from n? Okay, so basically, yeah.
Yeah, it is not needed.
Okay, yes. So basically, what are the things that we need to do over here? So first of all, one thing is getting the last number. So if I take any number, let's say 712, and if I want to find out the last digit, so if you divide it by 10, so I'll be getting what I'll be getting, let's say 7. So I'll be getting, let's say 10, 7. So I'll be getting 70. That would be 112. I'll be passing 1, 10 ones are 10. That would be. So basically, if you divide any number with 10, you'll be getting the remainder as the last digit. The remainder will be the last digit. Okay, because if you multiply anything with 10, then the last number will always be a 0. Right? So if the last number is not a 0, then you will get the last digit as the remainder. So so what I will be doing, I'll be just applying the modulo 10 in order to find out the last digit. So remainder will be nothing but the number n modulo 10 that will be giving me one of the digit. Now, after getting one of the digit, how to reduce the length, how to remove the last digit from a number? How can we remove the last number?
Divide by 10.
Divide it by 10. Yes, exactly. So mathematically, if you want to remove the last digit, if you divide it by 10, so what will happen if you divide it by 10? So basically, you can observe over here, the quotient what you are getting, it does not contain the last digit, right? So that is, if you divide the number and take the quotient, that is basically the last digit will be deleted from it. So the next function call that I will be doing, just a minute. So the next function call that I'll be doing, let's say if I want to find the answer of fun of n. So for that, I will be having some variable, let's say n modulo 10. So I'll be getting the last digit, right? So this will be my last digit plus what I will be doing over here. I will be calling fun of n divided by 10. Okay. And that value is the sum of digits of n. Okay. And now over here, the base condition. What is the base condition? Like the smallest problem for which you already know the answer.
And less than 10.
And less than 10. So what will be the answer for
And itself.
n itself? Okay. Yes, exactly. So basically, whenever you divide any number, let's say if this is a, and if you divide a by, let's say, b, and suppose the value of a is lesser than b, then the division, what will the division give you? The number itself, a, right? Yes or no? If you divide 1 by 2, what you will be getting? Like basically you get nothing. Like the integer value that you will be getting will be 0. You get the number itself. Or you apply the modulo as well. Let's say if you do 1 modulo 2, what do you get as the answer for modulo? The remainder comes out to be the same number itself, right? If you do, let's say 9 modulo 10, what do you get? You get the same number, right? So if the value of n is lesser than 10, okay, so at that point you can simply return that number in itself. Because if you divide a number, so over here 1 divided by 2, the integer value that you will be getting will be 0, because the answer that you will be getting is 0.5 and the integer division gives you 0. So whenever there is a division a divided by b and the value of a is lesser than b, you will be getting 0. Okay. So I've handled this condition over here. For all the values that are lesser than 10, I know the answer. That is going to be the number in itself. So this is the recursive algorithm for finding the sum of digits. Any confusion in this? Which projects should I build for guaranteed 8 LPA web development? So Ayush, basically what you need to do for getting placement, obviously a general scenario for everyone. Okay, so nowadays, earlier when Corona was going on, and earlier, let's say back in, let's say 2022, when the question was asked, like let's say, is DSA enough for getting placements at that time? Yes, DSA was sufficient for getting placements, but now the companies have understood, like basically they are considering DSA as a standard thing that every computer engineer should know. Okay, so along with only DSA is not going to help you. So projects are required. So what kind of projects for web development? So start with the basic problems, like basic projects. So, and the best project that you can do is create your own portfolio, right? And if you are interested, first of all, web development, try to figure out front end or back end. Okay. can we convert this into tail recursion? So do you think how can we convert it? Do you think can we do it? So yeah, Mahesh is saying that can we convert it into tail recursion? So I want some answers from you guys like afterwards. So first of all, let me just get the solution of this using recursion. So if n is lesser than 10, I will be returning what? The number itself, right? And what else I will be doing? Let's say if this is n and then right? So I'll be returning, let's say first of all, I'll be finding sum of digits of n divided by 10, removing the last number, and what else I will be doing? That is n modulo 10, the last digit. Yeah, so can we convert this into tail recursion? Okay, so that's an interesting thing. Can we do? Anyone? I want answers from you guys. What do you think? What about tail recursion for this?
Yeah.
Okay, so what will be that approach of tail recursion? Anyone?
Okay, so if we will pass the result as the parameter.
Pass the result as a parameter.
Yeah.
Okay, and yeah.
So instead of returning the result directly from here, we can just call the function with the and modulo and divide by 10, and whatever the and modulo 10, we will pass it in the parameter to the function itself.
Yes. Or instead of doing that as well, what you can do outside of a recursion, you can have a variable that says sum. Okay, so will that work outside of the function if you have a variable? You need to add the value. No, I did not get you. Like if you pass it as a parameter, so how will that work? So n modulo 10, let's try to see. Let's say it is fun of 1, 2, 3. And in the parameter, I will have a sum variable, or let's say it is initially 0.
Yeah.
So fun of 1, 2 will be called, and the last number 3 will be added over here.
Right.
Okay, and fun of 1, 2, and 3. Let 1 will be called, and the 2 will be added over here. So 3 plus 12 modulo.
3 plus 2 will, so it will become
So 3 plus 2, 5 will be
5.
done.
Yeah.
So yeah, that will work perfectly fine. So so what the approach which we have got from the is that basically you can have one more parameter over here. So integer n, and along with this you can have a sum variable that will store the answer. So if n is lesser than 10 over here, so you can simply return basically n plus sum. And what else you can do? You can add a return statement over here, that is fun, and divided by 10, and sum plus and modulo 10. So whenever the next function will be called, whenever our next function will be called. So over here, may understand this thing. So all the operations before calling this function, the parametric operations, whatever parameters, these operations will be performed, and then the function call will be done. Okay, it's not the case that function call has been done and afterwards, whenever required or something like that, this parameters will be calculated. No, it will not be the scenario. It will be calculated. So when the parent function is basically called again, nothing is remaining for the function to execute. Everything has been executed. So this is a tail recursion. Okay. So what about the time complexity over here? So what do you think? So for this, what do you think will be the time complexity? Order of n log 10. Okay. Log n. Order of length of n. Yes. Log n. Order of number of digits. So over here again, we'll analyze how many times the function is called. Okay, so if we draw a recursive tree for this, it will be fun of n. Next function will be called for fun of n divided by 10. Next function will be called for fun of n divided by 100 or something like that, because this is n divided by 10 divided by 10. So that would be n divided by 100. Again, this fun will be called for n divided by 1000. And so on and so forth till what? Till the value of n, basically, if n divided by some 10 to the power k will be equivalent to 0. Right? So that is the value of n is lesser than. So that is what I have written over here, 0 or something like that. Okay, so how many times this is calling? Like how many times this is being called? So instead of 0, if I write down 1, then also it will work because base condition will be hitting at 1 as well, right? So the value of n is reducing in this manner, n divided by 10, then n divided by 100, then again n divided by 1000, again n divided by 10,000, so on and so forth till the value is a single digit. Till the value is a single digit. So what is this? I can rewrite this in this manner. So if I can say this is n divided by 10 to the power 0, this is n divided by 10 to the power 1, n divided by 10 to the power 2, n divided by 10 to the power 3, n divided by 10 to the power 4, and this is nothing but n divided by 10 to the power k. And this gives me a single digit. Okay, this is a single digit. And I'm considering it as 1, the last number that I'll be getting. So if I want to find out, how many times this is being taking place. So you can observe it is being executed how many times? K plus 1 number of times, because 10 to the power 0, 1, 2, 3, 4, and 10 to the power k. But so can I say order of k is the time complexity? No, I cannot say order of k. So what do you think this will be equivalent to? Basically, you can observe that at each and every step, you will be deleting one digit. So at the end, 0 digits will be present, or a single digit will be present, right? So the total number of digits that are present at that many times this function will be called. And if I want to write down in a mathematical and find out the value of k, so what you can do, this is n divided by 10 to the power k. It will be reduced down to 1. Okay, so this can be any number. Okay, it can be 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Any number, the last number. So I took 1 over here. So n is 10 to the power k. I'll be taking log base 10 because I want to get rid of this 10 and I want to find the value of. So that would be k log 10 base 10. This will be 1. So k comes out to be log n base 10. So the overall time complexity, to be precise, it is log of n base 10. And this value for simplicity is called total number of digits. Right? Yes. So all of you who said log n base 10, log of length n, like basically order of length n, Order of number of digits. Yes, exactly. You all of you are correct. So what about the space complexity of it? Constant? No, not constant, Mahesh. Same as complexity. Yes, so the space complexity is also equivalent to basically number of digits, just like the time and space. Both of them over here is order of number of digits. This is the space complexity over here. Can you explain? Okay. Yes, Navneet Patak. Yes, exactly. Okay. So yeah, let's move forward and let's is my screen stuck or is it visible? Okay, I hope it is visible. Yeah. So let's understand a very interesting way. Yes, Madan Chopra will be next question that we are encountering, that we are taking, is a medium level question, right? So this is an interesting technique, I would say, and not a question, because this technique will be helpful to you whenever you need to find out the power of a number. Okay, and trust me, this is very much efficient and it is a very much so-called intuitive approach. Like uh, a good observation will give you a better approach for finding the power of numbers. So try to just quickly read the problem statement. 1 to 2 minutes are enough, and then I'll be explaining what it is uh, trying to say and basically what we are supposed to do. Just a quick yes or no in the chat box if you have read the problem statement. Just write down +1 or just notify me in the chat box if you have read the problem. Okay. So we have a yes from Mahesh. So basically, in this, what we are going to do, basically, you'll be given a number and it's reverse. Okay. So what you are supposed to do, you're supposed to find that number raised to the power of its own reverse. So if n equals to 2 and r equals to 2, it is saying find 2 to the power 2. If n equals to 12, then the reverse of 12 is 21. So it is saying find 12 to the power 21. And the answer can be very large enough. So it is saying that print the answer with a modular 10 to the power 9 plus 7. That is what the question is trying to say. Okay. Okay, Navneet and okay, Madan. So first of all, let's go ahead with what is the basic approach that comes to your mind when you see finding the power. So basically, in this, if I write down the question in a single line, it is trying to say you have to find out x to the power n. And n is what? N is nothing but reverse of x, integer value. So let's say I can say it is 2 to the power 2, you will be finding out 4. If it is 12 to the power 21, whatever is the value, that will be over here. If I say 1, 2, 3 is the number, you will be finding out 1, 2, 3 raised to 3 to 1 and 1, whatever is the value. So that is what the question is trying to say. So how to find out basically x to the power n. So x to the power n, we need to understand what is this value. It is x into x into x into x. How many times? N number of times. This is the value, right? So over here, just like the factorial, I can use this value. I can just find x and I can find out x. What I can do, I can write down fun of x and n minus 1. So if I want to find out fun of x to the power n, I can write down in this manner. So what I have written over here, this is basically if I want to find out x to the power n, I can multiply x with x to the power n minus 1. For x to the power n minus 1, I can write down x into x to the power n minus 2, right? So the basic approach, if you keep on multiplying, it will be taking order of n time complexity. That n times you will be multiplying a number x, right? But now anything advanced, anything observable or a good observation from whatever relation I have written over here, can we optimize this to something better? So Madan says x to the power n minus 1 into x, and the base case for power. Yes, Madan, you are correct. We can do in that manner. But here I'm multiplying n number of times. So I want to work something like that will take less amount of time. So what can I think of? Any observation? First of all, I need to know some observation. What have you observed over here? Okay, Tanishq, yes, exactly. For even, okay. Could you explain the note of the question? Okay, yeah, Himani, I will explain note of the question. Okay, okay, Tanishq, exactly, Tanishka, yes, exactly. So anyone else? So if you have any kind of solution, I would suggest directly ping it to me instead of writing it to everyone. So no worries, from next time, just mark this point. Okay. Okay, so let's try to observe what we can do in a better manner. Okay, so note of the problem. So yeah, let me just explain. Okay, so in the note, it has been mentioned that print the answer with print the modulo 10 to the power 9 plus 7. So what it is saying, trying to say basically, whatever result you are trying to get, it is going to be greater. See, whenever you see any kind of statement like this, as the answer can be very large, print the result modulo 10 to the power 9 plus 7 or something like that. So at that time, understand first of all, whenever you apply, let's say if the number, if you have any number num, and if you do num modulo, let's say 10, then always the answer is going to be in what range? It is going to be in the range 0 to 9. And let's say if I use, let's say 70, num modulo 17, then always the answer is going to be from 0 to 16. Okay, it can never be 17 or greater than 17. If I write down num modulo 10 to the power 9 plus 7, then the answer is always going to be in the range 0 to 10 to the power 9 plus 6. Okay, so your answer will be a very small value, like a value in this range that is accommodable, that can be accommodated in any of the integer values. Okay, so that is what the question is trying to say. I hope it is making sense now, Himani. Okay. So the observation over here, a very nice observation. And in this also, I will just take this question to some more, like, let's say, optimize. Like this question was asked to one of my friend in the interview as well. Okay. So this is not a very simple question, or it is very much famous, like from interview point of view, this question. Try to find out power of any number. So over here, let's say if I want to find out, let's say 2 to the power 8. So I'll be doing 2 into 2, and again I'll be doing 8 number of times. Right? So this is what? This is nothing but 2 to the power 4. And this is what? 2 to the power 4. Okay, fine. So if I have the value of 2 to the power 4, I can simply multiply the value of 2 to the power 4 again, and I can get the value of 2 to the power 8. I will, let's say, store it inside some temp. Then 2 to the power 8 is nothing but 2 to the power 4 multiplied by 2 to the power 4. Okay, fine. So what is special if I take an odd number? So odd number, this will be 2 into 2 into 2. Right? This is 2 to the power 4. This is 2 to the power 4. So in case of odd, when the power is odd, you have an extra element, you have an extra number that needs to be multiplied with 2 to the power 4 and 2 to the power 4. So as I mentioned, this will be a temp. So 2 into temp into temp. So what I'm trying to say, first of all, what I will do, let's write down a recursive code. Let's write down recursive code in which we are finding the answer in a linear manner, in a so-called, let's say if r equals to 0, then I will be returning 1. And I'll be returning n into power of n comma r minus 1. So this is nothing but n multiplied with power of n to the power r minus 1. Okay. This is a simple approach, and let me just change this value x and n. So this will make much sense. X to the power n. Okay. So this is x multiplied by x to the power n minus 1. So now this makes much sense. So I'm trying to find x to the power n. So this is an approach. Okay. So now let's get back to the observation that we are seeing right now. So let's say, as I mentioned, I will not do things twicely. In case of odd, I have observed that there will be an extra element that needs to be multiplied. But in case of even, I can see temporary value which I get by dividing the power is what I need to multiply it again. So let's say if I am supposed to find out to the power 9. So I have 2 into 2 to the power 4 into 2 to the power 4. Now what is this power 4? So this is even number of times. If you divide 9, if you divide any odd number by 2, you will be getting an even number. Like let's not take an even number, but I'm just taking half of the numbers that are supposed to be multiplied. Now what I will do again, I will try to find out the answer for 2 to the power 4. So that would be 2 to the power 2 and 2 to the power 2, half of the numbers. So now 2 to the power 2 is nothing but 2 to the power 1 and 2 to the power 1. And 2 power 1, if the power is 1, I can simply return the number, or I can say this is 2 to the power 0 into basically the number in itself. 2 into 2 to the power 0. So what I have written over here, this is odd number of times multiplying an extra element and finding out this is 2 to the power 0. So basically, at each and every step, I simply need to find out the power answer of, let's say if x to the power n is to be found, and let's say over here is equivalent to x to the power n by 2 into x to the power n by 2 if n is odd, I mean even. And it will be equivalent to x into x to the power n by 2 into x to the power n by 2. In which scenario, if n is odd. So now by writing down the recursion of it, we'll be able to observe that how is it impacting the time complexity. Okay. So how will it impact the time complexity if we try to observe? So over here, half of the task is already done. So how the half of the task is already done? Basically, if I get the value of x to the power n by 2, I don't need to find out again x to the power n by 2. So if I want to find out fun of x to the power n, then what I can do, I can just go and find out fun of x to the power n divided by 2. I can find out this value. And again, whatever is this value, let's say this is my temp. I have found it. And again, I will multiply that value with itself. Okay, so if I write down the recursive approach of it, so that would be looking something like this. X to the power n. So over here, each and every time, you simply need to find out the power of n divided by 2, whether it is even or odd. See, over here, you are finding out 2 to the power 4, even number of times. This is x to the power n. N is equivalent to 9. You have removed the number, you have converted it into integer numbers. How many total count? The count is integer count. So dividing it equally and finding out the answer for the smaller problem, half of the problem. So fun of x to the power n, basically, I will focus on the base condition afterwards. So let's try to write down. So I will call the function again and find out fun of x to the power n divided by 2, and I will store it inside a temporary variable, whether it is even or odd, because I know this value needs to be found. Now what I will check if the number n, basically, let's say if the number n is even number, n modulo 2 is even, then what I will do? I will simply return temp into temp. I will simply return temp into temp, because temp is what? It is x to the power n divided by 2. And if it is odd, if the number is odd, that is the power is odd, then what I need to return? I need to return the number x multiplied by temp into temp, because the temp which I have written over here is nothing but x to the power n divided by 2, and this is x to the power n divided by 2, and this is x. This is x to the power n divided by 2, x to the power n divided by 2. Are you getting my point? What we are doing over here? Everyone, yes or no? A quick response in the chat box. And so if I talk about the base condition, see, one more, we have encountered a different question. So I would like to add one more observation to find out the base condition, that observe what values are being changing, like what values are changing over here. So one of the observation to find the base condition is the smallest problem for which you already know the answer. Answer should be always known for them. Or the other one is that check which parameters are changing. So both of them go parallel to each other, smallest problem and which parameters are changing. The parameter n is changing over here. N, first of all, it was n, then it become n divided by 2, then it became n divided by what? It will be n divided by 4 and n divided by 8 and so on and so forth. So at the end, what do you think? It will be n 2 to the power k, something like that. So why 2 to the power k? Basically, I wrote 2 to the power k, basically 2 to the power 0. It can be written as 2 to the power n divided by 2 to the power 2, and in this manner. So I wrote down the last statement as n divided by 2 to the power k. So the smallest thing that I'll be getting over here will be that I'm dividing n by something that will give me 1 over here, right? So if the base conditions, I can write down the base condition over here in this manner, that if my n basically reduces down to what? What do you think? What should I write down? One. Okay. Okay. So Himan is saying 1. Okay, 1, not 1. Anyone? So like, what will be the base condition? I will keep on dividing n by 2, keep on dividing n divided by 2, n divided by 2. So basically at the end, it is possible that it will be reduced down to so-called 1, or it is possible if the number is 1, let's say if n is 1, then 1 divided by 2. It is possible, no? See, both the things goes parallelly. I said no, smallest problem and check which parameters are changing. So the question can be that smallest problem is like x to the power 1, or let's say it is 1 to the power 1. So over there, if you divide 1 divided by 2, you will be ending up with a 0, right? Okay. So I'll be adding out that if the power is 0 over there, at that time, I will be simply returning 1. Okay, so this is going to be my base condition. Yes, exactly, Darshan. Okay. So how is this impacting my time complexity? So the other approach which we wrote was basically, first of all, it will find the value of n, 1 of n, then n minus 1, then again n minus 2, then n minus 3, and so on and so forth till 1. So now over here, the value of n is being reduced by 2. So what do you think log n base 2? Okay, yes, exactly. So this is very famous sequence. In the binary search as well, you might have observed this sequence, right? So the time complexity, if I keep on linearly multiplying the elements, comes out to be order of n, and the space comes out to be order of n. And now over here, if I keep on multiplying the value, this comes out to be log of n base 2. And space complexity as well comes out to be log of n base 2. Why n base 2? If you find out the value, the sequence, that is n to the power k equals to 1, apply logarithmic on both the sides, k will be log n base 2. Okay. And in the interview, like they might start up with how to find out power of, let's say, x to the power n, and they are expecting this approach from you. Okay, and this is very much faster compared to order of n. Obviously, you are reducing half of the task, right? So yeah. So after writing the solution, now what the next thing the interviewer can ask you? So first of all, let's write down the solution and let's try to complete the optimal approach. So if n equals to 0, I will be returning 1 over here. And I will be using long. And to store the value, I will be calling it as temp power of x and n divided by 2. Okay. And I will be checking if n modulo 2 equals to what? 0. I will be returning temp into temp. Else, I will not add the else condition, but if the number is odd, that is power is odd, I will be returning x into temp into temp. And to keep in mind the note which was written over here, that is modulo 10 to the power 9 plus 7. So where can it overflow? Like where should you apply this modulo 10 to the power 9 plus 7? So when the multiplication takes place, see, where do you think multiplication is taking place? The number is increasing, right? So if I talk about integer multiplication, integer into integer will give you an integer. Long into long will give you a long. But that number can be greater than 10 to the power 9 plus 7. So the answer, I will apply modulo over here. That is, let's say, modulo mode. So let me create a variable that is called mode, and I will be calling it 10 to the power 9 plus 7. Now, what about this kind of multiplication? So in this kind of multiplication, in which you have 3 different multiplications, so at each and every multiplication, you have to apply modulo. So x into temp, I will apply modulo. And after getting this result, whatever is this is the result, it will be multiplied with temp. And after multiplying with temp, I will apply a modulo over here as well. Okay, so for at each and every multiplication, at each and every step where the number is expanding, I will apply mode. So the number will be in the range 0 to 10 to the power 9 plus 6. And let's try to submit. Yeah. Okay. So is this question clear? Any doubt in this part? Anyone? So, so there is other way of writing. See, sometimes what the other approach. I'll write down one more approach. So let's say instead of doing power of n divided by 2, if I write it down in this manner, instead of temp, I use this everywhere, basically. So this does not make any kind of sense. Why it does not make any kind of sense? See, if I'm calling the function with x to the power n by 2, so basically I am again and again doing the same task, no? So basically this is not logarithmic of n. Basically, यहाँ पे what you are trying to do, see, the number of recursion which you are doing over here is more compared to the number of function calls which you were doing in the solution that we saw just now in this solution. There's only a single function call, but over here you are again and again calling the function. Okay, so both this does not mean the same. So one more interesting question. So try to read the problem statement of it, that is reverse a stack. So the main intention of this, like why I'm taking the stack quotient with recursion. So with the help of this quotient, you will understand recursion in a very better manner. So whenever you see recursion, imagine that you have a stack that is running in the background. So whenever you want something that is like, let's say, something similar to a stack data structure, but you don't want to create a stack, at that time you can think about recursion. So when do you think about stack? So in the questions in which you want to reverse something, if you want to reverse a string, if you want to reverse an array, you think about stack, right? Last in, first out. It can give you the elements in reverse order. Same way, recursion can help you to get the reversal as well. So this question is basically saying that you have to reverse a stack. And what I am expecting, basically you have to reverse the stack using recursion. So what do you think? So if the stack is 3, 2, 1, 7, and 6, so 3 is the bottom of the stack, and this is 6 is the top of the stack. So after reversal, 6, 7, 1, 2, and 3 is the answer. So I want your inputs that what do you think? How can we reverse a stack using recursion? Any ideas like how can we reverse a stack using recursion?
So pop all the elements in the recursion and at the end start inserting the element again in the same stack.
Pop all the elements from the stack.
Yeah, one by one in the recursion, and when the base condition reaches, it returns. So we will start inserting the data again in the stack.
So in what manner will we insert the elements? That is, yeah. So let's say
Last in, first out.
last in, first out manner. Okay. No, I'm not asking that, but let's say this is stack 2, 3, and 1. Okay. So let's say this is stack 2, 3, and 1. So over here, you will be having, let's say you will remove 1. Okay. So element 1 will be present, and again you will be calling function with 2 and 3. Okay, so this function call is with 2 and 3. And again over here what you will be doing, you will be removing the element top element, and the function call will be done with last element 2. And this is fun of 2. And element 2 will be removed, and now nothing is present, empty stack is there, so base condition. So I have removed all the elements. Now what should I do?
Right.
So yeah, sorry. So Jay, it is like we have two stacks. Okay. So the current stack where you have the elements 2, 3, and 1, we are popping them and we are storing them in another stack.
No,
Okay.
sorry, two
And the
stack.
other stack would be like once we pop, for example, 1, that would be stored as the first element. Okay. In the second stack.
Two stacks, like are you considering the recursive stack as well, right?
Yeah. So initially, okay. So consider we have only one stack. Sorry, 1 minute. Yeah. So we have this current stack now with 2, 3, and 1. Okay.
Yes.
We will be we'll have another stack where we store all the elements that we popped from this stack.
Okay, so we will store one by one. Okay, so let's say this function was called, so 1 will be pushed over here, and this function was called, then 3 will be, this function was called, then 2, in this manner.
Correct.
Okay, and
we just pop it, and
this can be your answer, right? We already reversed the stack.
Correct.
Yeah, we can do that. But I want to do it without using an extra stack. I want you to find out a solution that uses a recursive stack, that takes the help of the recursive stack. This is approach. Yeah, this is work. The auxiliary space over here will be somewhat more order of n.
Yeah, order of n, correct.
So let's try to observe a few things. Okay, so in this question, I will draw the recursive stack again. Okay, so like we'll observe with the help of recursive stack. This is my recursive stack, and this is my, let's say, original stack. And the elements are 1. What are the elements? 1, 3, and 2. Let's say 2, 3, 1. Okay, so I will call the function. I will call the function once, and in this function, so let's say function will be called, and the element that will be removed in this function at this point, that would be 1. One element was popped. So stack contains what? It contains nothing. So now function call will be done again. And now one element will be popped from the stack, that is going to be 3. Okay, fine. Now again a function call. So basically 3 will be popped from the stack. Again a function call. So fun. And now 2 will be removed from the stack. So now the stack is empty. Okay. And now when the again a function call is done, nothing is present inside this stack. So as this stack is empty, now I need to reverse the element. Now if I take this element and put it as it is, no, basically that would be 2, 3, and 1. Again the same thing. So now you can observe there are two different stacks. If you have two stacks, you can reverse the original stack. How to reverse it? So for this element, what I will do, whenever I want to insert anything, at each and every point, I have all the elements separated, right? at each every recursive call. Now, if I want to insert 2 inside this stack, what I will do? I will insert 2 at the bottom of this stack. This is my input stack, and I will insert this 2 at the bottom. I will insert the 2 at the bottom of this stack. So how will I insert the element at the bottom of this stack? So one thing what I can do over here is that I can create one more temporary stack. Okay. So let's imagine with the help of a temporary stack, and then we'll get rid of temporary stack as well. So I want to insert now, again, this function will be executed. Okay. So I want to insert it. So all the elements will be popped and pushed it inside the temporary stack. Nothing is present, and then 2 will be inserted. Okay. So that is how I insert the element again. Now this has been executed. Now fun of 3. So first thing I will be doing in this temporary stack, I will put all the elements. So 2 will be inserted over here. And now the element 3 will be inserted. So 3 will be inserted. And now again back all the elements. So 2 will be again pushed inside this stack. Okay, so now this has been executed. Now this needs to be executed. So 1, before inserting all the elements, put it over here. That is 2 and 3. So now the stack is empty. Now push 1 inside this stack. Again, push all the elements. So that would be 3 and 2. I can do in this manner, right? Do you guys agree with me that this is the process? I am using a temporary stack. And the insertion I am doing is at insert at bottom. Every time I'm doing this process. Okay, the link of the question. Yeah. So is this like making sense what I'm doing over here? Right. So I'm using an extra stack over here. So how is it different from the approach? Like this is kind of more complex than what we heard right now, right? So basically it is better to take a different stack and each and every point insert it inside the stack. So now in order to get rid of this temporary stack, what I will do, I will use recursive stack over here. So you might be wondering, how can we use recursive stack? So again, writing down the state which was there, that is fun of, and over here 3 will be present, and then fun of 2. Okay. So now everything has been separated. Now again, the execution of this function starts. Okay, now I need to insert it inside this stack. So I will call one more recursive function, that is, let's name it as insert at bottom. And this is the recursive stack of the insert at bottom function. So what this function will do, whatever elements are present inside the stack, it will separate all the elements. So let's say the name of this function is B. So the B function will be called recursively to remove all the elements. So no elements are present right now. So the stack is empty. That is going to be its base condition. When the stack is empty, push the element inside the stack. So 2 will be inserted. So don't worry. After this stack gets populated, you will understand it in a better manner. Now, next is this function. Again, the execution takes place, resumes the execution. Now 3 wants, I need to insert 3. So what I will do, recursively, I will make function calls. So bottom function will be called, and 2 will be removed from the stack at this point. So 2 will be removed from the stack. Now again, bottom function will be called. Okay, now bottom function says nothing is present inside this stack. So you can insert 3. So this 3 will be pushed inside this stack when the stack becomes empty. Now, again, whatever elements were removed, so 2 was removed. So 2 again will be pushed inside this stack. Okay, so I'm inserting at the bottom. I'm taking the help of the recursive stack over here. Okay, so now function element 3 has been inserted. Now moving on forward, I want to insert 1. Again, the inserted bottom will be called. So now the top element will be removed. So 2 has been removed. Again, a function call. So bottom function call 3 has been removed. Nothing is present, but again a function call. Now in this, the stack is empty. So I will insert 1. So 1 has been inserted. Now again executing this function. So this function inserted 1. So executing this B of 3. So inserting 3 back to the stack. So it has been executed. Now a B of 2. So inserting 2 back into the stack. And now 2 has been executed. And now this fun 1, basically 1 was supposed to be inserted. So it has been inserted. So originally this stack was 2, 3, and 1. Now I have reversed it using one more recursive function. Is it making sense, or do you want me to explain with one more example?
I think some code procedure would help us understand it better.
Okay.
But I think the time complexity will take a beating here, right?
Okay, we'll analyze the time complexity, but yeah, let me take one more example. So let's say the
Explain with the code. One more example, I think it will be better understandable.
okay, explain with the code. Okay, just a minute. But
You
yes,
that is unable to imagine how it will be inside the code.
your voice is not clear, Satish. Can you please repeat?
The new function, that p function you have, right? That unable to identify where we can paste it in the code.
Code. Sorry.
Now, basically, what he's saying is we are not able to follow through like exactly how it would be implemented in the by writing code. Okay. So if you can give a code example that whatever you just explained, okay, that would make us understand better how the recursion, how exactly we are calling this recursion. We are removing the previously added element, okay, and then appending one more thing, and not exactly appending, but that process.
Okay, so yeah, we'll come to that part. I will not directly jump to the recursion and explain how the recursion is working, because yeah, so that will not help you to develop any. So I will come to that part, but once again the procedure once again, and then it will make more sense. So basically, at each and every function call, I have a function over here. Okay, so in this function call, I will pop the element from the stack. So the stack contains, so okay, so this is 3, 2, 1, 7, and 6. Okay, so this is my function fun, and this is my different function bottom function. Okay, so if I write down the body of this function, so this function takes an argument that is our stack. Okay, so what this function does, it removes an element. So let's say it is an integer element. Okay, so it will pop the element. Let's say pop one of the element from the stack. So before popping, we need to check if the stack is empty or not. So if stack is empty, then you don't need to pop. You have to simply return, right? Okay, fine. So this part, and now what I will be doing, I will be making a function call, and that function call will be with some different values. So this much part, what I am doing, I will just explain it. Okay, so function call, element has been removed from the stack. So the top element that will be removed, it will be stored inside the element. So state will be stored, as I mentioned, right? So 6 will be stored. Now again, a function call will be done. So the stack has removed 6. So again, a function call. Right? So now over here, 7 will be removed. Again, a function call. Then over here, element will be 1 for this function call. Again, a function call. Element 2 will be present. So it has been popped. Now again, a function call. And element 3 will be popped from this stack. Right? Now at the end, if I call the function, the stack is empty. So I will return. So I will return. Now, again, the execution of this will take place. Again, the execution of this function will take place. Now the stack is empty. So the next line that needs to be executed is over here. So what is that next line? I will call the function that is insert at bottom. So what I want to insert at bottom, I want to insert the element which has been removed over here inside the stack at the bottom. Okay, fine. So our next recursion has been called over here. So how will this insert at bottom work? So this insert at bottom, what will it do? It will take the argument stack. So insert at bottom, what it will do? Similarly, let's say, similar to this function, it will keep on removing the element. So integer element, it will pop the element. It will keep on removing the element, and again, it will call insert at bottom for this type. Okay, fine. So when will I insert the element? So over here, we'll be having two arguments, that is the stack and the element that I'm supposed to insert. So when should I insert the element which I am supposed?
Jay,
Yes.
at this stage,
Hmm.
when the insert at bottom will be called after the recursive calls.
Sorry.
Okay,
When?
okay, yeah, you just updated the code. I got a little confused then.
Yeah.
Yeah.
Yeah, Jay, I still, don't understand this concept, because anyway, we are having a second stack and we are storing all that info in a duplicate memory, right?
So see, this is not, I'm not saying this is an optimal approach or it is beneficial. But the entire solution that we are writing is using recursion and no extra space apart from recursive stack we are utilizing. So that is the intention of this question, and that is what the problem statement is saying.
Mm-hmm. No,
So
I'm
the
just
recursive stack doesn't
trying
come
to
under auxiliary space. So
Yes.
Oh, sorry, I couldn't follow that point. So, can you please, move it to the left where we are storing this info, not the function. Like there is a stack that we populated, right? Yeah, this one. So this would take some space, right? Calling these recursive functions, or storing this info like 6, 7, 1, 2, 3. Like this one would take memory, right?
Yes, it will occupy memory. Recursive stack. Yes.
Yeah. A
but
recursive
that's
stack does
recursive
not.
stack. That is part of any recursion execution, isn't it? It's not about the recursive function space. It is any recursive functions that you call, it will be part of the recursive stack.
So it is auxiliary space is something that in order to solve the question, the logic that you are applying, what amount of space. So this is a process, recursive process, and along with the recursive process, you will have recursive stack. So you cannot get rid of this recursive stack. So generally, the space by recursive stack is ignored. But when we discuss the approach with the iterative approach, we also consider that, okay, stack is there, so space will be required. But when we just see recursion, at that time, we don't discuss the space occupied by recursive stack.
Yeah. Oh, okay. Understood. So we won't consider the space occupied. Okay. Yeah. Good. Thank you.
So Jay, so basically to solve it using a recursive stack, we are using an additional recursive method to
Yes,
do this.
exactly.
Okay.
So that was like I already before this I explained a reason. I explained it using a temporary stack, right? So in the temporary stack, what I was doing, all the elements of the stack, I was pushing it over here, and then whatever element was there, I was inserting it at bottom, right? So I was using a temporary stack. But now I'm not using any temporary stack. I'm just using a function. I'm calling a function, and that is a recursive function. So that function will act as my temporary stack. I'll show you both the methods in which I'm using stack, and I will write down. When I will complete the code, you will understand everything. Okay. So till then, wait a little bit. So X at each and every point inserted bottom, I have removed the element. Okay, I'm constantly removing the element and then calling this stack. Constantly removing and calling this stack. So when the stack becomes empty, at that point, at that time, you have to push the element x. Okay, and return from here itself. Okay, so I will return from here itself, because if you don't return, again the same thing will take place. You will remove the element, insert at bottom will be called, and so on and so forth. So now I have completed both the function. So now if we observe, see, this has been executed till now. Over here, till this much of part, we have seen the execution. All the elements were removed. This element ELE has the value of the element. Now insert at bottom is called. Okay, so insert at bottom is called for this function. So let's say to call insert at bottom. So bottom, and the element is what? 3. And the stack, what is present inside the stack currently? The stack is currently empty. So what is the base condition? If the stack is empty, push the element inside the stack. So 3 will be pushed inside the stack. So insert at bottom, what is its task? Its task is to insert the element at the bottom of the stack. So when the stack becomes empty, it will push. So that condition was executed. Now, this function has been executed because the last thing that this function does is call the insert at bottom. So now for this, it has been executed. So fun of 3 has been executed. Now again, this function will be executed. That is fun of 2.
In the second recursive method, push would be element, right? Not x.
Yeah, element. It will be element. So fun of 2 will be executed. Now fun of 2, I want to insert 2 inside this stack. So inserted bottom will be called for it. So inserted bottom, element 2, and what is there inside this stack? 3 is present. Now the stack is not empty, so it will put the element inside x, top element. So 3 will be removed and it will be inside stack. So after removing 3, our stack, which is over here, it contains nothing. So now a function call will be made in which I have to insert 2 and the stack is empty. So base condition has been executed, right? Base condition will be executed. So 2 will be inserted inside this stack and a return statement will be executed. So this execution of this stops. Now over here, resuming the execution of this function. So what was the process? So one more thing we need to add, that is after coming back from recursion, I need to insert the element that was removed, that is push x back into the stack. So this 3 will be pushed back inside the stack. It will be pushed back inside the stack and it will return back. So the execution of this has taken place. So it will be removed. So now this function was executed. Insert 2 at the bottom has been done. Now insert 1. Now this function will be executed. I have to insert 1 at the bottom. So bottom function will be called. Now element is what? I have to insert 1. And the stack contains 2 and 3. And over here, one element will be popped. So 3 will be popped. And a function call will be made, right? So 1 I have to insert and the stack contains 2. Only 2 is present. So 2 will be removed over here. And now again a function will be called and the stack becomes empty over here. Nothing is present. So when the stack becomes empty, push the element. So 1 will be inserted inside this stack. Okay. Now this condition was executed. Now again, going back to the execution of it. So over here, after calling the insert at bottom, next line will be executed. That is push the element inside this stack. Which element? Which was removed. That is 2. Insert it back inside this stack. Okay. Now this function has been executed. So now 3. For 3 also, insert the element which was removed. So 3 will be inserted inside this stack. Now is it making sense? Let's see one more time so it will be clear. So this has been executed. Now this will be executed. Fun of 7. So for fun of 7 means that I have to insert 7 inside the stack. inserted bottom. So fun of 7 inserted bottom will be called. So its recursion is over here. B of 7 and the elements are what? 1, 2 and 3. So first element will be popped, so 3 will be popped, and again a function will be called, that is B of 7, and what is present? 1 and 2. Okay, so this is now again an element will be removed, so 2 will be removed, so 2 will be removed from the stack. And see over here, observe, see, this is the stack, this is the original stack, and the elements that I am removing, they are now present inside the recursive stack. They are present as a state of this recursion. Okay, and now again calling the function, and now the elements that will be present will be a single element, that is 1. Again remove the element, so this element will be removed from the stack and it will be stored in at the state of the stack, at some state. Okay, and now B of 7, and now nothing is present inside the stack. When the stack is empty, insert the element. So what was the element? That is 7 was supposed to be inserted. 7 has been inserted. Now again this will be executed. So basically after coming back from recursion, next line that will be executed is push the element that was removed. So which element was removed? 1 was removed. Push it back inside the stack. So 1 will be inserted back into the stack. Now this has been executed. Again for it, now insert back 2 inside the stack. Okay, insert it back. Now next thing again, insert 3 back in the stack. So inserting 3 back to the stack. Okay, so this has been executed. Now for this, the last thing, fun of 6, that means inserted bottom will be called for this 6. So I have to insert 6. So inserted bottom. So I have to insert bottom. I have to insert 6. Now I'm not drawing this tag. Okay. So top element will be removed. So 3 will be removed and it will be present over here as a state of this tag, as a state of the recursion. Now 6 has been 6 is supposed to be inserted. So top of this tag will be removed. So 2 will be present. Again B of 6 and remove the top of the stack. So 1 will be present over here. The top of the stack has been removed. Again calling the function B of 6 and the stack will be there. So 7 will be removed and it will be present as a state of the recursion. And at the end, B of 6 and empty stack. When the stack is empty, insert the element. So 6 will be inserted. Okay, so this function, its execution is complete. Now for this, what will be executed? Basically after coming from the recursion, push the element that was removed. So which element was removed? 7 was removed. So push it inside the stack. 7 is been inserted. Execution completed. Now for this, I have to insert 1 back in the stack. Insert 1 back into the stack. Now for this, what I have to do? I have to insert 2 inside the stack. Insert 2 inside the stack. Now what I have to do for this? I have to insert 3 inside the stack. So insert 3 inside the stack and execution is complete. And this has been executed, this function. So remove this from the stack. So what was the original stack? It was 3, 2, 1, 7, and 6. Now this is our reversal stack. Now is it clear? Is it making sense now?
Yep.
Okay. So let's try to code this solution. Okay. So yes. So this is a reverse method, right? So what I will do, I will use this reverse method in itself. So this is going to basically, first of all, remove the elements from the stack one by one. So let's say integer element is equal to s dot pop. It will remove the element and again it will call reverse and stack has been called. So I need to add the base condition. So if the stack is empty, say is empty, If the stack is empty, what it will do? Basically, this is first time I'm removing the elements from the stack. So I'll be just returning from here itself. So after returning, at each and every point, elements are present. So now the element needs to be inserted. So I will call insert at bottom. See, this element was removed from the stack. Recursion was called. Now I need to insert this element again inside the stack, but I have to insert it at bottom. So I will call insert at bottom recursive function. Insert at bottom. So this is the element and this is my stack. So when should I insert the element? When the stack is empty. If the stack is empty, at that time, you have to insert the element. That is ELE. And do not forget to return. Okay, if you don't return, you will end up in an infinite recursive calls. So if the stack is empty, I will return. Now, if the stack is not empty, I will put the element that is inside the state of the stack, that is inside the variable x. And again, call the method insert at bottom. I have to insert element, and this is my stack. So after recursion, when it comes back from the recursion, just like this reverse method, I will again insert it inside the stack. So I will insert the element that is x back inside the stack. See, both the functions are kind of similar. In this function, in this reverse function, basically, I'm removing the element from the stack. Inside the insert at bottom, before recursion, I'm removing the element from the stack. That is storing as the state of the recursion. Now I have to insert the element, right? So inside this reverse, after the recursion, I'm inserting the element at the bottom. So for that, I'm calling the insert at bottom. So this element will be inserted at bottom. In this part, it will be inserted. Now at insert at bottom, I'm inserting the element. This element, basically, whatever element was removed, basically that element is inserted after recursion is being called. See, this element ELE is inserted after the recursion is called. Similarly, this X is inserted after the recursion is called. Both of them are similar. This inserted bottom just adds an extra thing that when the stack is empty, this element will be inserted. Now let's say to compile and run, and let's say to see. It is working perfectly fine, and let's try to submit and see what is the solution, like acceptance. Okay, so the solution has been successfully submitted. Now any doubt in this approach, how we are reversing a stack using recursion? Any confusion, like just give me yes in the chat box if everything is clear.
Yeah, one doubt I have
Yes.
is you mentioned that if we do not keep that return in line number 68, it would go to an infinite loop, right?
Yes. Okay, so how will it go, right? Is it your question?
Yeah.
Okay, so at the end, in the last step, okay. So over here, if I don't add a return, so assume that the stack is initially empty. I mean, the stack does not contain anything. Okay. So if the stack does not contain anything and I am calling this function with insert at bottom 3, and this is my stack st. So what will happen over here? Assuming that this return statement is not there. Okay, so if this return statement is not there,
yeah, it will push to this particular stack, right? We are specifying the stack we want to push. Yes.
now again it will be popped from the stack. So basically, if I show you over here with this, it will make much sense. Okay, so over here, so basically the stack is empty and this is bottom. So 3 has to be inserted. Stack is empty. So what I'm doing, I'm inserting 3 inside the stack. Okay, fine. No return statement. Okay. So what does it mean? Remove the element. So over here, element 3 will be present as the state.
So it will continue executing the lines of code that is below this if we
Yes.
don't give return, and that will result in pop of the inserted element.
Yes.
Understood.
So at each and every state, again, the element, copies of the element will be stored.
Understood.
Yeah,
Okay.
you are inputting and again popping and storing it.
Okay, that goes to infinite loop. Understood. Thank you.
With Shubham and GFG IDs for some of the problems, C sharp is not coming as the choice of programming. Okay, so it is possible, Shubham, that that language might not have been added for the particular question. C sharp. Okay. In GFG ID or ID or
Yeah, in GFG online,
Acha,
we are executing.
into this ID online compiler.
No, not this one where we are solving the problem and submitting it. Yes. So
Yeah. Okay, yeah, C, C++, Java, and Python support will be there, but for C sharp, for some of the questions, it might not be there. Yeah. Okay, so this was all about recursion. We have an entry point to recursion, and tomorrow we will be solving questions on backtracking. Okay, so tomorrow we'll be seeing many different types of questions on recursion, because recursion and backtracking, if you observe over here, we have used backtracking. If you agree with me, if you know somewhat backtracking, then what I have done in reverse function and what I have done in insert at bottom, this is what backtracking is. So if you are not aware with backtracking, just yes, I have also shared so-called a Google sheet. Inside that I have linked each and every Google document of each and every lecture. Okay, Satish Kumar, yeah. I will ask Sumit just to share this sheet on the Discord channel as well. Yeah, Shubham. Okay. So in tomorrow's lecture, what will be my agenda? I will be taking more questions on recursion, and will be tomorrow will be seeing some kind of advanced, or let's say little bit tough questions compared to this. Okay, because recursion, basically if you directly jump into tough questions, it might not help you in developing the logic of writing recursion. Okay. So yeah, that was it in this session. I hope everything was clear, and for tomorrow's session, have a revision on the questions which are given to you. So basically the questions which are given to you in the assignment part of each and every topics on your dashboard. Try to solve these questions on recursion. Try to get your hands dirty with recursion. Okay. And all of you are watching us on YouTube. Yeah, you can go to the GeeksforGeeks practice section, practice part, and over there, just have a look at the basic to medium level of questions on recursion. Try to practice all those questions. And if you really enjoyed this lecture, do hit the like button and do comment down your like what is your strategy of writing down a recursion. Because I have seen like everyone follows a different strategy, and what is the strategy of writing the recursion, we'll discuss in tomorrow's session. Okay, so yeah, the feedback form has also been shared in the chat box, so do fill the feedback form. Okay, so that was it for in today's video. What are the questions for practice? Okay, so let me open this and just give you an idea. So we'll be having a recursion over here. So we have recursion. Inside recursion, go to recursion and solve at least from easy to medium questions. Okay, try to solve all the easy questions and basic, school, and easy. Try to solve all these easy questions. And if you are comfortable in all this easy, and if you have solved by tomorrow's lecture, then do solve one of the medium question. Okay. This is also a very good question. This uses backtracking, but recursion and backtracking both goes parallel. Okay. So try to solve all the easy and basic or school level questions that are mentioned in this problems list. And if possible, then go ahead with medium questions as well. Okay, Mahesh? Yeah. Okay, so bye-bye everyone. Let's meet tomorrow, and we'll be having a few more interesting questions on backtracking in tomorrow's lecture. Okay. Bye everyone. Bye-bye.
Thank you.